Good morning, Astronomy 1020. We have all the tools that we need to prosecute a successful class today. We have coffee and we have the Casio FX260 Solar. Your fingers are going to get a workout today on this little machine. Let's think about where we left off last time, shall we? I believe I asked you guys to calculate the force of gravity between the Earth and the Moon. But of course, that's only interesting if you have something to compare it against. So, I don't know, let's start by sharing a screen. I wanted to hunt for this, but I was too busy making coffee. What if we just look up a picture of Earth, Moon, and Sun? Normally I like to use globes, but my screen is a little cramped here. So, I don't know, let's take this picture here, I guess, although I can imagine a better one. Actually, here, let's start here. What do you suppose is stronger? The force of gravity between the Earth and the Moon, or the force of gravity between the Earth and the Sun? If you had to take a guess. Oh, here we go. This ought to do. Hold on, someone's chatting me here. What's our chat box say? Kevin says Earth and Sun, and Caitlin agrees. Well, I guess that's a decent guess. What's cool about Newton's law of gravity is we can answer such questions directly by calculating them. And let's remember where we were last time when we ended class. In our last class, we calculated the force of gravity between the Earth and the Moon. And do you guys remember the value that you got?
Two times 10 to the 20th.
I need some units on that, homie.
Newtons.
Correct. 2 times 10 to the 20 newtons worth of force. Suppose the Sun and the Earth gravity is stronger. What's the cause of tides on Earth? We live in the ocean state. Tides are part of our everyday lives. Caitlin says the Moon. Okay. And the Moon causes tides because of gravity, right? The gravity of the Moon, says Arunsak. Well then, why doesn't the Sun cause tides if the Sun's gravity is stronger than the Moon's?
Is it too far away?
But do we not include the effects of distance in our calculations? After all, let's
can, but doesn't distance, since distance, it's distance squared, so doesn't distance have a bigger effect on the equation than mass would?
Well, but then in a way, mass is squared as well because it's the mass, it's the product of two masses. If you hold one mass fixed, then what you're saying is correct. Distance does have an important effect because of the square. We're going to make some hay out of that, actually. But it's not about the distance and mass go into the calculation of the force of gravity. You guys suspect that the Sun-Earth gravity is stronger than the Earth-Moon gravity. But then it's not distance that causes tides, it's gravity that causes tides, right? So why isn't the Sun causing tides if its gravity is stronger? Shouldn't there be?
Well, because it's too far away, right?
Yeah, but distance gets, I think you're missing my point. Distance gets factored into it. You know what? Why don't we calculate it? Let's calculate it and then we can talk about it, all right? So your first task for me today is to prove that you can still handle doing this, okay? Let's start with a sample problem and let's find the Sun to Earth gravity by comparison. Let's first make sure that your suspicions are correct, okay? So you're going to need some givens to do this. You're going to need to know the mass of the Sun. I'm going to introduce some symbols that you're going to see me use from time to time. I need a little more board space here, so let me tuck this away. So this is the Earth to Moon gravity. And I'm going to tuck that away up here as 2 times 10 to the 20 newtons. Hopefully, yeah, you guys can still see that. That's good. All right. And I'm going to give you some givens. This is the mass of the sun, 2 times 10 to the 30 kilograms, where I've introduced the astrological symbol for the sun, a circle with a little dot in it. So you'll see me use that in place of the sun quite often. There's also a symbol for the earth. It's a circle with a cross in it, and I want to get you guys accustomed to that right now. So this is the earth, okay? The mass of the earth is 6 times 10 to the 24 kilograms. And what's the distance between the sun and the earth, students? That's something I would expect you to know. One AU, says Devin. Devin, do you have that in any other unit? The distance is 1 AU. What is 1 AU? Sometimes you guys talk to me, sometimes you chat me. Okay. Do I have to look at 150 million kilometers, says Kevin. I like it. That's how we were taught in our previous lectures. Okay, so let's look at the force of gravity. The force of gravity between the sun and the earth will be big G times the mass of the sun times the mass of the earth divided by the distance squared. That's Newton's universal law of gravitation, right? Are we ready to plug our numbers in, or do we need to do something first? Geez, you guys look even more sleepy. Oh, a Runsack. Correct. A Runsack says we have to convert the kilometers to meters. He's good. He knows what to do. But I can't. A Runsack, do you want to talk to me? Do you want to walk me through that? Since you're so damn good? Or yeah. Okay, Runsack, time to turn that audio back on. Time to talk to me.
Hey, you.
Tell me how to do that.
You start with the thing you want to convert.
Okay, so what do I write down?
So you want to convert the mass of the sun first.
No. You just said meters. That's what you said.
Yeah.
A mass is, right?
So you're converting the 1 AU, so the 150.
Just tell me what to write down.
150 times 10 to the 6 km.
Correct. Now what do I do?
X bar.
Yep.
You got your U.
Whoop. We're losing you. Sounds like you said units. Is that what you said?
Yep. Yeah.
What units do I want?
KM bottom and meters up top.
Do you know the conversion?
Yep. It's 1 to 1,000. 1 up top. I mean 1,000 up top and 1 to the bottom.
Right, and then we cross out our kilometers. Hey, I bet you could do this in your head. 6 zeros, 3 zeros, what's that going to turn out to be? No calculator required.
9. So 150 times 10 to the 9.
Look at that. A Runsack is so good, students. He doesn't even need a calculator because he knows he's going to add 3 zeros to 6 zeros. And yet, Christopher just gave you a round of applause there. Okay. Nice. A Runsack, you are good. You rock. So you can mute yourself. Let's go ahead and put this into our law of gravitation now. So our force of gravity, I'll put my units in blue, will be big G, which is always 7 times 10 to the negative 11 meters cubed per kilogram per second squared, times the mass of the sun, 2 times 10 to the 30 kilograms. Sorry, it's kind of noisy downtown, but I wanted the window open. Times the mass of Earth, 6 times 10 to the 24 kilograms, all divided by 150 billion meters squared, excuse me. Okay, I'm the operator with my pocket calculator. It's time for you guys to punch it up. let's have a little fun here. Well, who's sniffling? Okay, Chris, that looks good. What can you tell me how to round that up? Keep it interesting for me.
We're rounding up to 1 sig fig, correct, or 2?
Yeah, keep it fun, keep it simple.
All right. So would it roughly be 4 then?
Okay.
4 to the times 10 to the 22 meters per second squared, correct?
Let's see. Meters cubed cancel with meters squared,
Okay.
leaving 1 meter behind.
Oh, it's newtons, sir.
Yeah.
Sorry.
It's actually kilogram meters per second squared, which is a newton. 4 times 10 to the 22 newtons. So Chris, is the Earth, wait, let's see if I can get them both in the frame here. What did we determine, students? Is the Earth-Moon gravity indeed weaker than the Earth-Sun gravity? Were we correct? Yes, we were correct, Caitlin. Hey, Caitlin, suppose I asked you how many times stronger the Sun-Earth gravity is than the Moon-Earth gravity. No calculators, though. You can't use a calculator. Do you know how to do that? Yeah, you do. Okay, hold on a sec. Let me show you how we compare, all right? And the whole purpose of this is to not use a calculator. We're going to compare. You guys will remember that in this class, compare always means take the ratio. So I'm going to divide the force of gravity between the sun and the earth by the force of gravity between the moon and the earth. And I'll have 4 times 10 to the 22 newtons over 2 times 10 to the 20 newtons. Newtons cancel. Caitlin, 4 divided by 2. Oh, you don't want to talk to me today? You just want to chat me? Oh, there you are.
Sorry, my like mute thing wasn't coming undone. 2.
2? Okay, I'm sorry. I missed what you said, but you sound perfectly good to me. Do you know how to do this? You subtract the powers.
2.
So what is that number?
2 times 10 to the 2.
Right, but you know, what's that number? What is the number? What is 2
I'm gonna
times?
go out on a limb here. 200.
Yeah. What does it mean?
Oh, it is 200. That the sun is 200 times stronger, like gravitational pull, than the moon to the Earth.
Exactly. 200 times stronger than the moon. Nicely done. Oftentimes, if you put numbers in scientific notation and you round them to one significant figure, it becomes very easy to kind of roughly compare their strengths. So you guys actually had pretty good intuition. You suspected that the sun's gravity is stronger than the moon's gravity, and you were correct. The sun exerts 200 times more gravitational pull on the Earth than the moon. So let's get back to that question I asked then. If the sun's gravity is stronger than the moon's gravity, why is the moon causing tides and not the sun? Now, I don't know if it was Kevin or Runsack or whoever was chatting. All right, Caitlin. So Caitlin says the moon is closer, but Caitlin, did we not account for distance in the law of gravity? You see what I mean? It's like you could say, well, it's not distance that causes tides. It's the force of gravity. And we accounted for the fact that the moon is closer in the law of gravitation, and the sun's gravity was still stronger because the mass of the sun is so much crazier than the mass of the moon. Well, the moon is smaller, but the size of your masses, actually, okay, so it turns out that the size of your masses does have something to do with tidal forces. And one of the issues is when we calculate the force of gravity between the sun and the earth, the distance is so much greater than the size of the objects that we can often sort of neglect the size of the objects. Let me share my whiteboard screen and show you what we're actually doing. When we calculate the force of gravity in this way, what we're doing is we're assuming that the sun is a little mathematical point source, okay? It's a little dot. And we're assuming that the earth is a little, is a little mathematical dot. We're not thinking about their sizes, and we're thinking of the distance as, imagine if you had two little microscopic black holes and they were separated by some distance d. That's sort of the way we're computing them, the force of gravity. But let's take a think about the size of the objects for reals. So the Earth, I've never done this on the whiteboard, but I'm going to try to do this. The Earth is a sphere, okay? And the radius of this sphere is 6,400 kilometers. So the diameter of the Earth is, let's see, 12,800 kilometers, right? So that's the size of the Earth itself. And now the Earth is separated from the moon by, what is it, 384,000 kilometers? Just bear with me here, students. I usually do this on the board, but I need a lot of board space for this. So I'm trying this out on the whiteboard here. So let's see if I can choose, I don't know, yellow for the moon. Actually, let's just forget about the moon for a second. Let's ask ourselves this question. If we consider the diameter of Earth as a fraction of the distance between these two, what percentage of the distance to Earth Moon does the diameter of Earth make up? So you guys know how to do that, right? Like, if I leave this, will it be there when I come back? I hope so. Let's take some notes on the tidal force and see how it works. Okay, this section of your notes is on how tides work. And it's going to turn out that we need to know about this not just because tides on Earth are interesting, but tidal forces play a big role in all areas of astronomy, from things that happen in our own solar system to stars going into orbit around a black hole. All of these objects experience tidal forces. Oh yeah, Arunsak, that's where we're going with this class. You might think of all the stuff you're learning is building up towards us having a really cool discussion about black holes. And that's going to come as we get further along in this class. We're going to talk about weirder and weirder things, and it's going to get more fun. But right now we got to build up your science muscles, okay? So let's start by saying this. Tides are caused by gravity. But the tidal force is not the same as the gravitational force. So the tidal force is a little different than the gravitational force. We would say that the tidal force is here's your $10 phrase, okay? It's a differential force that acts over an extended body. Tidal force is a differential force that acts over an extended body like the Earth or the moon. To put it yet another way, you could almost think of the tidal force as a delta force, okay? I ain't talking Chuck Norris delta force. I'm talking about the difference between the force of gravity on the front versus the back of an object. This is a sort of simplified version of it. If any of you out there may have, Austin, it's not so much, it's not the orbit like going around in a circle. The tidal forces would exist, Austin, even if Earth and Moon were stuck in place and were not swinging around each other. So tidal forces do not require, nope, rotations have nothing, well, rotations do affect tidal forces, but rotations are not necessary for tidal forces. So you don't want to start off by thinking about rotations. Let me give you a moment to just get this into your notebooks because I need to do some drawing. I'm a little too awkward with the whiteboard, so I'm going to have to do this here in real life. Can I erase this or does someone need a moment? Chris, you writing? Oh, you're good? Is everyone okay? Okay, Austin, let me know when you're good, buddy. Yep. Austin, Runsack, you good? Okay, Cameron's good. Austin, all right, Runsack's good. Austin, all right, you're good. Okay, so let's start with a picture here, okay? So Earth is a sphere, and the Moon is a sphere that's 384,000 kilometers away. The diameter of Earth is 12,800 kilometers. Let's start by taking out our calculators and asking ourselves, what fraction of the Earth-Moon distance is the diameter of Earth? So what percentage of the distance between them is the diameter of Earth? To do that, we'll do 12,800 kilometers divided by 384,000 kilometers, and punch it up and tell me what you get. Mixed up. Anyone? Okay, Caroline, but the fun is for you to tell me the answer using your words. Fun for me anyway, it's not for you. What'd you get?
0.03.
Let's leave it there. So 0.03. And what does that mean, Caroline? What does 0.03 mean? What did I do with, oh. See, let me put it this way, Caroline. I think of every number that's between 0 and 1, anytime I get a number that's between 0 and 1, I always think of it as a percentage. That's how I think about it in my mind. So what percentage would that be?
3.
3%.
Point.
Yep, you just moved the decimal place twice. That's 3%. And the way I interpret that, Caroline, is the front of Earth is 3% closer to the Moon than the back of Earth. Let's imagine I had a gigantic planetary-sized cheese grater, and I was going to slice the Earth up into thin slices of Earth cheese. All right? So first I'll take a really thin slice somewhere towards the front of the Earth, and this slice will have a small but finite mass. And then I'll take an identical slice of Earth cheese somewhere near the back of Earth. And I'll slice them in such a way that they are both equally thin, and both of these slices have the same mass. Probably a mixture of rock and metal is what these slices would be made out of. The slice on the front of Earth is 3% closer to the moon than the slice on the back of Earth. And that means I could actually calculate a force of gravity between the moon and these cheese slices. The force on the front would obviously be stronger than the force on the back, right? I just want to make sure you guys understand that. Why would the front slice be stronger? Why would the force of gravity that the moon exerts in the front slice be stronger than the back slice?
The distance.
It's closer, right?
Yeah. It's
Hey, if you're
closer.
really good, if it's 3% closer, by what percentage will the force of gravity be stronger? That might be too much for you, but it's an inverse square law, right? No. If it's 3% closer, it'll be 9% stronger. Because the force of gravity, we're going to do this in our homeworks today. The force of gravity is inversely proportional to the square of the distance. So if you're...
I remembered that from before, and that's what I was trying to explain with the distance squared thing, but you know, I had my wires crossed.
Yeah, well, you were onto something, but it's nuanced. And right now we're trying to break down the nuance, right? Let's put some cartoon numbers on this if we can. I'm just going to make up the numbers. These aren't the actual numbers, but whatever. Let's imagine that the force of gravity on the front slice is 40 newtons. And that means I've sliced this so infinitesimally thin that it came out to be a very small number of newtons. The back slice might experience something like, well, if it's 9 or 10%, it would be 4 newtons. Fine. So maybe 4 newtons, right? And that means the Earth is experiencing a tidal shear force, a pulling apart, a delta force or a tidal force of 40 newtons minus 4 newtons, something like 36 newtons. And this 36 newtons is felt across the diameter of Earth as if it was a teddy bear being pulled apart by 2 stubborn children, okay? It's the front, both slices are being pulled in the same direction, but if this slice is being pulled 36 newtons stronger than the back slice, as far as the Earth is concerned, it's just feeling a sort of shear force pulling it apart. Let's look at a little cartoon of that. Hold on a second. I'm glad to know that that sticks around if I want to use that again. Slideshow. Okay, so here's 2 pictures of how the tidal force is working. The Earth is experiencing a stronger tug on the front side of Earth than on the back side of Earth. But from an Earth-based reference frame, this manifests itself as a shear pulling apart force that creates 2 high tides, one bulge in the direction of the moon, the other bulge is in the opposite direction of the moon because the Earth is being pulled apart. Another way to think about that is you could imagine the middle of Earth being pulled a little harder than the backside of Earth. But in any case, it squishes the sides of Earth down into 2 low tides, and it pulls the oceans into 2 high tides, one that faces the moon, one that faces away from the moon. Not only does the ocean experience high tides and low tides, the atmosphere of Earth also bulges in the direction of the moon. And believe it or not, the ground rock underneath your feet actually is deformed by about 3 centimeters each day in the direction of the moon. The very ground that you're standing on is actually deformed, and it morphs the Earth so that it's no longer a perfect sphere, but it gets stretched into a slightly football shape that we call an oblate spheroid. It basically warps the very rock underneath your feet. Let me just check that chat and see what. Well, Wyatt, that turns out to not be related to, on some planets, on some moons around Jupiter, the tidal forces can be so immense that they actually create geothermal activity. But as I explained in my Astronomy 1010 course, the geothermal activity of Earth has to do with several factors. One, the heat of accretion. When Earth formed, it starts off hot. But today, most of the geothermal activity is due to radioactivity in the ground rock and in the mantle. So it's actually, yes, Io, Cameron, very good. Io is the moon of Jupiter, which actually gets geothermal activity from tidal forces. Wyatt, what you are saying is possible in other places where you have a very massive planet and a sort of wimpy moon next to it. But the moon's tidal forces, although they do bulge Earth, the 3-centimeter bulge is not significant enough to generate a tremendous amount of geothermal activity. You get many more watts of energy from radioactivity than you do from tidal forces. So what you're saying is not crazy at all. It's a very plausible thing. It just happens to not, okay, yeah, I'm over-explaining this. It happens to not, yes, I did hear about the discovery of possible microbial life on Venus. That is a really wild discovery. What they found, let's just have a little science break here for a second. The big science news this week, if I share screen, I'll show you like an article in the Washington Post or something. Let's just go here. And they found a molecule called phosphine. Okay, so life, Venus, I don't know, we'll do Washington Post. There's many places we could. So they did spectroscopy on the cloud tops of Venus, and they found this element called phosphine. And to date, the only known source of phosphine would be some kind of microbial life that they are hypothesizing could somehow exist in the cloud layers of Venus. This is a pretty wild discovery because Venus was always thought to be extremely hostile to life. It's the same size as Earth, but it has like 10 times as much atmosphere, and it's hot, and the clouds are full of acid rain. Venus was always thought to be one of the most hostile places to life. So finding phosphine suggests that perhaps there could be some type of microbial bacteria that exist in the clouds, and that would be pretty wild. Well, Arunsek, I'll tell you what I think about aliens. There are what, 1 trillion stars in the Milky Way galaxy? And we now know that most of those stars have planets around them. So what's the probability of life existing in our own solar system? 1 out of 8 planets have life that we know of in our solar system, right? Yeah, it's just improbable. 1 divided by 8, let's do our percentages. That's a 12.5% chance of finding life on a planet in our solar system. Now suppose there are 1 trillion stars and each of them have 10 planets around them. That's 10 trillion, so times 10 exp 12. Okay, so we've got 1 trillion planets maybe that potentially have life. Yeah, so do I believe that aliens exist out there? Hell yeah, I do. Do I think they're coming down to South Dakota and making crop circles in Farmer Joe's cornfield? No. Do I think they built the pyramids? No. You know, like, I don't think they frequently visit us and impersonate our grandmother or something like that. They've got their, well, the part of the issue is just there are vast distances between places. Like, even traveling at the speed of light, it would take 4 years to get to Alpha Centauri. And that's a sort of technical limitation on how fast any potential being could travel. So the problem is we're all kind of like ladybugs on different islands in the Pacific, and it's not easy for us to get from one island to the other island. Well, look, so you guys are chatting me about this stuff. The people watching later are gonna have no idea what's going on here, but we're gonna talk about light in our next lecture. These questions will be better discussed when we actually get to stars. Right now, you only have little pieces of the puzzle. You need to start seeing the whole puzzle by building up things like this. In any case, before I get totally derailed here, the tidal forces are acting over this extended body of Earth and they're pulling it apart. And a student could ask me, well, what about the sun? Doesn't the sun also exert a gravitational force on the Earth? And isn't that force 200 times stronger than these forces? The answer is yes, But the issue is that the diameter of Earth is a much smaller percentage of the Earth-Sun distance. So in fact, if we were to do the same game for the sun, remember that the distance to the sun is 150 million kilometers. In fact, this will be a little test of how well you guys understand percentages. I want you to find the percent distance, or the percent that Earth's diameter makes up of the distance between Earth and the sun. So in other words, do 12,800 and divide it by 150 million. What do you get? Someone shout at me here. I'm not sure I understand that,
9.
Austin. What? Yeah, tell
9
me.
times 10 to the negative 5.
Correct, Christopher. Now, Christopher, can you tell me what that means as a percentage? What percentage is that?
Really small.
No, 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 no. Smaller than really big or bigger than really small? What's the number as a percentage? I know you can do this. Christopher, it may help to think that by moving the decimal place over twice to the right, you're going to reduce that number by 2. Okay, I got to close the window because there's too much traffic.
Professor,
Come on. So what?
Professor,
Okay, a runsack, that's what you wrote down. A runsack writes down what this number is. Yes, it's 0.12349. But who cares whether it's in scientific notation or not? I want to know what it is as a percentage. Christopher, do you understand me? Does anyone understand me? Am I
think
truly
so.
alone like the aliens? No, Caitlin, not 9%. That is not correct. Caitlin,
Like,
friends, we move the decimal place over twice. That's how we turn it into a percentage. So what's my percent? Yes, a runsack says 0.009%. How do I even say that in English? Yeah, Caitlin. Oh, you work at a bank? Well, then what the hell? Like, I hope I never have to go out for a beer with you, and you better not be leaving the tip if you can't do these percentages. Hold on. This is the 1,000th place, Austin. So how do I say this number in English? I want to see if you guys can do that. Oh my gosh, Austin works at a bank. Does anyone even go into banks anymore?
I work at a call center, so I work from home and I just take calls from people, not
Oh,
people
wow.
that actually go into the bank,
Hey,
which
where
are
my
just
money
old
at?
people. They get mad. They get mad that the banking centers are closed.
I used to actually, so the only reason I joined Bank of America is because I lived downtown and they used to be located in the Superman building, the Industrial Trust building. And it was the most beautiful place to do banking because you'd walk in and there were marble columns and all of these like frescoes on the wall. It was so beautiful. And they closed it down and I was like, I know, it's kind of like the Kmart of banks, but it's all right. You know what? I'm not going to go there. You guys are not going to get me off track. Anyways, how do I say this as a percentage using my words? I just want to see if you guys can do this.
I want to say 9/1000%.
That would be very good, Christopher. I would say it is 0.009%, but 9/1000 is also good. So it's, all right, I am not going to look at this chat anymore. 0.009%. So in other words, let's just put some cartoon numbers on this. If the sun is tugging on the front side of Earth, the force that the sun exerts on the front side would actually be stronger than the moon's. Instead of 40 newtons, it would be something like 400 newtons. But the force that the sun exerts on the back side of Earth would be like 399 newtons. And therefore, the difference in force between the sun tugging on the front of Earth and the sun tugging on the back of Earth is a change in force, or a delta force, of only 1 newton. Now try to understand what I'm saying here. What I'm saying here is it's possible to say two things that sound contradictory. The force of gravity that the sun exerts on Earth is at all points stronger than the force of gravity that the moon exerts on Earth. But the change in force, the tidal force that the moon exerts on Earth, is still stronger than the sun's tidal force, because there's a bigger gradient of force across the Earth. In fact, for those of you who may have had calculus, this is what a tidal force really is. A tidal force is a gradient of force. The tidal force is a gradient of force, of the force of gravity. Does anyone know what I mean by gradient? Does that term, I guess you kids might call it like a fade or something. The gradients can appear, it's a mathematical concept. Let's do a black to white gradient. This is what a gradient is, right? It's a mathematical change in values. Here it could be the intensity of pixels, right? So as we go from white to dark, the pixels could have a value of 100% all the way to 0%, and it's a slow fade. This is a concept that can appear in colors, it could appear in anything, but it's a mathematical concept. See, there isn't just one slice of cheese on the front side of Earth and on the back side of Earth. There are millions of little Earth slices, and each one of them is experiencing a slightly different gravitational force. This is what bulges and distorts objects. As an example of why tidal forces can be cool, in the case of Mars, Mars has this moon called Phobos. And Phobos is a small rock in comparison to our moon. It's only, I don't know, maybe 50 kilometers in diameter or so. So I'm not sure if it's Phobos or Deimos, but one of the moons of Mars is actually just on the edge of what's called its tidal disruption radius, where these moons can actually get so close to the planet that the difference in tidal force between the front and back side of the moon can become greater than the self-cohesive gravitational force. And these moons are on the verge of being pulled apart by their tidal forces. If you could look up at Mars through a telescope 1 million years from today, these moons would be ripped apart into a little ring of rocky debris that would surround Mars. So sometimes, yeah?
Isn't one of them also like getting closer to the planet, so it'll like crash into it at some point?
It will be tidally disrupted, Christopher, long before it crashes into it. Mars will pull it apart as a ring. In fact, that's one of the reasons why Saturn today has such beautiful rings, right? Saturn's rings are composed of chunks of ice that are sort of the size of like a compact car or something. And what you don't know is that Saturn is surrounded by dozens and dozens of small icy moons which are made of chunks of ice. And as they wander too close to Saturn's immense gravity, Saturn just rips them apart and chews them into little icy bits, which then orbit around the planet. So while it is possible for moons to crash into a planet, usually tidal forces actually disrupt them and cause them to break apart into little bits long before they ever hit the planet. Okay. Anyways, by the way, the sun does influence tides, just in case I don't get to make that point. Is any good cawhogger, who is our cawhogger? Was that Devlin? I don't know if he's here with us today, but I think this is the class where we had a cawhogger here. And fishermen know about spring tides and neap tides, okay? So twice a month, when the moon is in new moon or full moon phase, it's actually aligned with the sun, and you get stronger than average tides. And twice a month, you get something called neap tides. They're wimpier than average tides. And that's when the moon is at first or third quarter, and its tidal force is perpendicular to the tidal force of the sun. The sun's tidal forces is much smaller, but it has a mitigating effect on these tides, making them weaker. So I think you can actually look up like tidal variation in Narragansett Bay. And I don't know which one of these websites has it right, but you can actually see changes between spring tides and neap tides over the course of a month. I'm not going to get lost in this sauce here because I've already wasted too much time on it, but you'll just have to take my word for it. You can see examples of spring tides and neap tides if you just take a walk down by the shore and you keep track of the height that the water is against the rocks. You can see sort of like a dark, wet spot on rocks that'll show you where high tide and low tide is. I always notice it when I'm biking on the East Bay bike path because that's what I like to do for fun. And you just see evidence of tides all around you. It's very beautiful. Okay, so we're going to come back to tidal forces in a bit. Now we have to move on to a new module. We have to talk about things you can do when you combine Newton's laws of motion with Newton's laws of gravity. And let's see how we're doing on time here. This next section is going to be called Newton's version of Kepler's laws. You guys will remember that Kepler had derived 3 laws of planetary motion, which are still today very important to us. He described how planets orbit the sun, but he also described in general how gravitational objects orbit one another. He did not know about gravity when he developed these laws. He developed them by studying the orbits of Mars and kind of coming up with the mathematical formula. Newton did know about gravity, and he wanted to take his newfound powers of gravity and kind of reanalyze Kepler's laws. And when he did so, he discovered a whole bunch of secret dimensions or secret parts to Kepler's laws that no one had known existed before. So the idea, if I could put it down into words, is he took his laws of motion, of which perhaps the second law is the best example, force equals mass times acceleration, and he combined them with the law of gravity, which is F equals G M over D squared. And by putting these 2 laws together, he could analyze the orbits of planets and moons of any arbitrary size and distance. So remember that Kepler's laws, if I haven't stated this already, they only work for planets that orbit the sun. If you want to get technical, or equal mass star. But Newton found an improved version that would work for any 2 gravitational objects. Newton's version worked for any 2, I guess I'll say, gravitating objects in orbit. That sounds kind of funny, but whatever. They work for any 2 gravitational objects in orbit. Today, physicists refer to the Newton version, the enhanced version, as Newton's version of Kepler's laws. And they're so important to this class that kind of everything we've done up to now is building up to teaching you guys about them. We're still under this heading here, but I want to give you a moment just to kind of catch up on this. By the way, this is not a minor point. This is a major point for your exam because I'm going to give you different types of problems. Sometimes you can use Kepler's laws, and sometimes you have to use Newton's laws. And I'm going to teach you how to do that in a moment here, but this is an important point. It's not a small point. Christopher, give me a thumbs up when you're done so I can erase this stuff. You're done? Caitlin, are you good? Yep. How about you trolls in the background there? Are you done copying? Can I erase? Okay, Emily, I'll give you a little more time. Emily, let me know when you're good. What's an object in orbit that isn't gravitating? Also, what's antimatter? Actually, antimatter is going to be part of our lecture on the sun, so I am going to teach you about antimatter. I'll defer to chapter 14 for that. An object that's in orbit that isn't gravitating, Austin, would be an electron orbiting around a copper atom. It's orbiting, but gravity is not the cause. Does that make sense? It is possible to have orbits that are non-gravitational. Okay. Not at all. Well, stay tuned. You're going to learn about that too. Let me erase this. Okay. This is actually a good opportunity for you guys to refresh your minds on Kepler's laws, and we'll see how Newton improved them. So Kepler's laws are definitely going to be testable material. Who remembers Kepler's first law of planetary motion? So we're going to do what I call NK1. NK means Newton's version of Kepler's first law. So what was Kepler's first law? You have to be able to remember that before I can tell you how he improved it. It's hot. It's warm in here. No, Wyatt, those are Newton's laws. This is going to get confusing, Wyatt. There's Kepler's laws, there's Newton's law, there's Kepler's laws of planetary motion, there's Newton's laws of motion, and then there's Newton's version of Kepler's laws of planetary motion. It's messy. What was Kepler's first law of planetary motion? Had something to do with your lab this week.
The law of ellipses.
Yes, Stacy. And what does the law of ellipses state?
Planet orbits the sun on an ellipse with the sun located at a focal point.
Very good, Stacy. Okay, so here's the deal, Stacy. Let me grab my lecture notes here, okay? This is what Kepler envisioned: a planet orbiting the sun on an ellipse with the sun located at a focus point. And that's fine when you have a big fat sun and a little tiny planet. But Newton now realized that it would be possible for different types of objects to exert gravity on each other and go into orbit. For instance, one classic example would be Pluto and its moon Charon. If you've never seen a picture of them, well, you should, because they look pretty wild. The New Horizons mission brought us extremely high resolution images of Pluto and its moon Charon. Here's one that I like. Charon might be a moon or a satellite of Pluto technically, but Charon is actually quite similar in Pluto in terms of size and mass. I think Charon is like maybe half or a third of Pluto's mass. So much so that some people think of them more as a binary planet system than Pluto is the planet and Charon is the moon. These objects are quite similar in mass, and they both exert tremendous gravitational forces on each other. See, what Newton was worried about is what would happen if instead of a planet orbiting the sun, what if you had something like a binary star system, right? Let's see if I can use the whiteboard for this. All right, can I clear everything? Yeah, okay. So let's grab our star maker here. So here's star 1 and here's star 2. And it's going to turn out that binary stars exist in abundance in the Milky Way galaxy. If the stars have equal mass, would we expect star 1 to orbit star 2 on an ellipse with star 2 at the focus point? Or would star 2 orbit star 1 on an ellipse with star 1 at the focus point? Who orbits whom when you have a binary star system? That's a question that Newton needed to address that Kepler could not. Do you guys know what happens?
The focus point is in the middle, in between both of the stars.
That's correct. What if they're not exactly equal in mass? What if it's a situation like...
Then it'll drift towards the object with the more mass.
Is that Wyatt?
Yes.
Damn, son, you're good. That's right. In fact, this is the concept that Newton improved on. The two objects will orbit what we call the center of mass, okay? The center of mass. So let me show you the slideshow again. Just a moment here. I got too many damn tabs going here. So there's a couple of different dimensions to this, but let's just start with the concept called the center of mass, which is what Wyatt is talking about. And his intuition is right on point. If star 1 and star 2 are equal in mass, the center of mass is exactly in the middle. If star 1 is, say, 4 times as massive as star 2, the center of mass will drift to 1/4 the distance from star 1. If star 1 is 10 times more massive, the center of mass will be 1/10 of the distance between star 1 and star 2. Now, in the case of the sun and a planet like Earth, the sun is literally 1 million times more massive than Earth. And that means the center of mass of the Earth-Sun system is actually 1/1,000,000th the distance between Earth and the sun. But now, guys, let's put some numbers on that. You guys know that 1 AU, right, is 150 million kilometers. I'm going to try to draw this with my mouse. It's not going to be pretty. Here's 150 million kilometers. What is 1/1,000,000th of 150 million kilometers? That shouldn't be too hard, right? What's a millionth of this number?
150
kilometers, right? Okay, but the sun's radius, let's just get out of here for a second. The radius of the sun is 700,000 kilometers. So if the center of mass is 1/1,000,000th of an AU, the center of mass of the Earth-Sun system is a point somewhere inside the belly of the sun. And let's think about what that means for a second. The Earth does not orbit the sun on an ellipse with the sun at a focus point. The Earth orbits a point inside the belly of the sun on an ellipse. And guess what? The sun also orbits a point somewhere inside the belly of the sun on an ellipse. Or in other words, the sun wobbles on its axis due to gravitational tugs from the other planets. And here's a little animated GIF showing you a hypothetical circularized orbit where Earth and sun are orbiting a common center of mass. In fact, here it's actually been exaggerated. And you can see that the star is actually wobbling on its axis from the gravitational tug of Earth. In our own solar system, we have 8 planets to contend with. And the sun's first order wobble is caused by the planet Jupiter, which is the most massive of all the planets. So Jupiter has the greatest effect on our sun's wobbling. After that, Saturn and the Earth are sort of tied for second place. So Saturn and Earth have a kind of equal effect on the wobble. And then all the other planets are like a third order wobble. So the sun's not just doing a simple wobble like you see here. It's actually wobbling around in a kind of chaotic rosette pattern due to the gravitational tug of wars that all of the other planets are exerting on it. This is actually really cool, and it has cool applications for modern astronomy. You guys may realize that we've discovered planets outside of our solar system, right? Does anyone have a rough idea how many planets that we have confirmed exist outside of our solar system? This is a big deal for me because when I was a student, a lot. Well, that's helpful. Why? Like when I was a student, the number of planets that we knew to exist outside of our solar system was 0. The first extrasolar planet that we confirmed, we found in the 1990s, like 1995, I think. Today, Wyatt, there are over 5,000 planets known to exist outside of our solar system. Now, we don't just look through our telescope to see these planets. Not happening. They're too far away, they're too small. You don't look through the telescope and see the Ewoks dancing around on Endor. That's not how this works, okay? The way you discover planets outside of our solar system is you take a telescope like the Kepler Space Telescope and you stare at a star for days and days and days at a time, and you wait for those stars to do a little wiggle. And based on the amount they wiggle, you calculate the existence of the hidden planets next to them. So we use this fact to, that's one of the methods that we use to find planets outside of our solar system. Okay, so I think it was Wyatt who understood the concept of center of mass. Here's something else. What if the orbits were not circular? What if they were ellipses? Can you guys try to imagine what that would look like? Because it's a little bit goofy. Let me jump ahead to a later a later lecture on binary stars. I have an animation here that would show you what it would look like if you had 2 equal mass stars that had highly eccentric orbits. And just give a second for this slideshow to launch here. Okay, it's slide 94. I want you guys to watch this. Hopefully this comes across the internet okay. This is what it would look like if you had a pair of binary stars in high eccentricity orbits. You'll notice that both stars orbit on an ellipse. The center of mass is the focus point, but interestingly enough, the first star is orbiting focus point 1 for the second star, and the second star is orbiting focus point 2 for the first star. So they kind of overlap their focus points. It's also beautiful because they're doing this this synchronized figure-8 dance. They always keep the center of mass in between them on a line, and they have a closest approach, we call that periastron, and a farthest approach called aphastron. No, a runsack, as we talked about in our first lecture, it's actually stupid hard to get things to collide in space because the orbits are so much bigger than the targets, right? Like, stars almost never collide in outer space because they would have to have trajectories that would kind of put them dead on alignment with each other. If the 2 objects are even offset by a tiny bit, they'll spin around each other and go into orbit, and it's extremely difficult to get them to collide with each other because the diameters of the stars are so tiny in comparison to their separations. It's extremely rare to have things collide at least in stellar astronomy. Of course, in our own solar system, meteoroids strike the planets all the time because the planets are, well, the meteoroids are spinning around the sun for sometimes billions of years before they eventually do hit the planet. But it's not as easy for things to bump into each other in outer space as you might think. Granted, stars probably have collided in the history of the universe, but it's a very low probability event, all right? Another thing to think about, let me show you guys an interesting video, actually. How many of you, have you guys ever been to the Boston Museum of Science? Oh, Christopher, you'd love it. Okay, so Caitlin has, and Chris has. One of my favorite parts of the Boston Museum of Science is going to the Mathematica section because they have all these cool, like, math models and toys and props. And there's one in particular that I'll probably return to in a later lecture. There's this thing called the gravity well. Let's see if we can find a YouTube clip of this gravity well. Once I show you the video, you'll know what I'm talking about if you've been to the Museum of Science. It's this thing. So this is actually in Hong Kong, but they have a similar one at the Boston Museum of Science. Let me mute this. They start off with this curved funnel, and they drop some ball bearings into the gravity well, and sure enough, they actually orbit the center on Keplerian ellipses. And if you were to analyze the motion of these marbles here, or these ball bearings, they're actually traveling on ellipses. The only reason they eventually in-spiral to the center of the gravity well is because there's friction between the ball bearing and the plastic cone. There's not a lot of friction, so they orbit for a long time, but eventually they lose energy and in-spiral towards the center. So Arunsak asked, do I ever worry about these stars crashing into each other? The difference between this and two stars in orbit, Arunsak, is there's absolutely no friction as they travel around each other in outer space. So they don't have any loss of energy that causes them to in-spiral towards the center. Next time you go to the Boston Museum of Science, spend a few minutes looking at this gravity well. You'll find it a lot more interesting than you may have beforehand. Okay, so how do we write down Newton's version of Kepler's first law? We would write it in the following way. Two objects orbit each other on ellipses with the center of mass at a focus point. So this is the improved version of Kepler's first law. In fact, we're not quite done tinkering with this thing yet. Newton discovered one more secret about this law. And the secret was that the orbits do not always have to be ellipses, but in fact, the orbits can be a number of class of shapes known as conic sections. Now, hear me out on this, because I'm going to get a little mathematical with you here for a second. Take a look at this slideshow here, and let's get rid of that one. Let's keep that one. And let's ask ourselves, how many ways can you slice a cone? There are 4 different ways to slice a cone. If you slice a cone perfectly horizontally, you get a shape called a circle. That's a possible gravitational orbit. If you slice a cone at an angle, you get a mathematical shape called an ellipse, and that's also a possible gravitational orbit. Kepler knew about these 2 things. Here's what he didn't know. When you slice a cone through the bottom, you get an open mathematical shape called a parabola, and when you slice it perfectly vertically, you get a second open shape called a hyperbola. Newton discovered that gravitational orbits did not have to be bound, but that there were possible orbits where a high velocity planet or star or comet could actually swing past the sun, have its trajectory bent or deformed by the gravity of the sun, and then the object can slingshot off of the sun and be flung out into outer space, never to return. There are a class of comets which come from the Oort cloud in our solar system, these long period comets, which sometimes pass by the sun and just get flung out into deep interstellar space, never to return. In a way, it's kind of like the sun and Alpha Centauri throwing snowballs at each other. Austin, it depends which scale size of space you're talking about. If you're talking about the Milky Way galaxy, most stars are bound to the gravity of the Milky Way. In our own solar system, the planets, the asteroids, and the Kuiper Belt comets are certainly bound to our sun's gravity. It's not so easy to say most things are not bound or they are bound. It definitely depends on which size scale you're looking at, whether you're talking solar system, whether you're talking galaxy, or whether you're talking multiple galaxies. Yeah, Austin says, I believe that in between the stars, there must be stuff hidden in interstellar space. And I think you're right. I think there's probably all kinds of dark planets and massive objects. The problem, Austin, is you can't just make shit up in science. Otherwise, you're a guy drinking the beer at the bar who goes, let me tell you about the president. I know what's going on, right? That's not how science is supposed to work. You have to be able to collect data and prove this. So while we may suspect and hypothesize that there are objects like asteroids and comets in between the stars, you have a burden of proof where you have to be able to detect them. And that could be, you're the guy, my uncle. Yeah, everyone's got a guy like that, right? Hell, I've been that guy, right? Okay, let's talk about Kepler's second law before I get sidetracked into any more of this nonsense. What's the second law of planetary motion that Kepler had? What was Kepler's second law of planetary motion?
Law of equal areas.
The law of equal areas. Okay, and the law of equal areas states an object, a planet sweeps out equal units of area in equal intervals of time. The short and dirty version of this is equal areas in equal times. Weirdly enough, when Isaac Newton analyzed Kepler's second law of planetary motion, he discovered that this law was true, no cuts, no butts, no coconuts, and it did not need any modification. But he also discovered there was a reason for it. And the reason that he derived was something called the conservation of angular momentum. Now, I have a really jazzy lecture on the I wrote that really badly. Conservation of angular momentum. I'm going to save this description for our next class because I really want to get to Newton's version of Kepler's third law. So this is a whole bag of beans that we have to unpack and take a look at. But I want to save that, and don't let me forget to, because I've got a cool demo to show you guys. I've got a really jazzy demo, but we're going to cover that next time. And the reason why is we need to get to the third law, which is the most important for our homework today. And I want to do that before I totally run out of time. Okay, I'm going to need a lot of board space for the third Newton-Kepler law. So make sure you got all this down because I'm going to erase. The harmonic law, Caitlin. And Caitlin, how does the harmonic law go? I meant to look up. So Caitlin's saying Kepler's third law is the harmonic law. It's a mathematical equation, and how does it go?
It's P2 equals A cubed.
P squared equals A cubed. Hold on. Class, may I erase this? Please say yes. Okay.
Yeah.
All right. If not, grab it next time. Caitlin, we need to do a kind of comparison between Kepler's version and Newton's version. This next law is really important for our homework and for our exam. So there's Kepler's law, and Caitlin says P squared is equal to A cubed. And what are the units? What are these things and what are their units?
Are you asking me?
Sure. You're talking to me, so what the hell?
Right. Where did that go? Just got rid of that page too. Okay, 1 second. I'm so sorry. Okay, so P is equal to years, and
It's
then
measured in
A,
years.
measured in years, sorry. And then the A is for AU.
Okay, and what do these things represent?
A period of planet in years for P.
A period, right?
Yeah, and then A is the semi-major axis or the average distance.
We'll just shorten that to distance. So A is the distance to the planet, P is the period of the planet. And they have to be measured in years and AU. Okay, here's the deal. This formula works only for orbits around our sun. In other words, it will work for planets, it will work for asteroids, and it will work for comets. It will not work for moons. It will not work for moons because moons don't directly orbit the sun. They orbit the planet. It also will not work for binary star systems. Or someone mentioned in the chat the Great Attractor. The Great Attractor is a cluster of galaxies that it's this gravitational force that all galaxies are being drawn towards. They are also in some type of Keplerian orbit. It won't work for those because that's not an orbit around the sun. Newton discovered that he could make a beefier version of this. And he could get it to work for any two gravitating orbits. But the math got a little bit, how should we say, juicier, okay? Introducing what we call Newton's version of Kepler's third law. Kind of a big deal. Newton's version of Kepler's third law. Because it's a lot of words to say Newton's version of Kepler's third law, from now on, this formula will be known as NK3. That's going to be our nickname for it, so that we don't have to say that every time. NK3, one of the most important formulae in all of astrophysics. It goes like this. P squared is equal to 4 times pi squared times a cubed divided by big G times mass 1 plus mass 2. So the idea is you've got two masses, M1 and M2, and they're orbiting each other with some distance in between them, which is A, okay? Here, the units are going, so by the way, can you notice the similarities? You still have P squared, you still have A cubed, but now you're accounting for the effects of gravity with 4 pi squared over G times the sum of the masses, all right? Let's talk units. P is the period. It's now going to be measured in seconds. A, the distance, is now going to be measured in meters. And the masses will now be measured in kilograms. In other words, this formula is an MKS formula. You'll remember we call this system of units the MKS system. All right, we need to try a sample problem with this because it's going to appear in our homeworks.
Professor, where does the 4 come from?
Well, the short answer is calculus. During the derivation, is that good enough? That basically shut you down right there, right? You didn't want to hear any more after that.
Beautiful.
It comes from calculus, okay? I could say more, but I'm not gonna. By the way, anytime you have circles or circularized things in mathematics, pi always shows up there. Because there are so many circles in astronomy, pi just kind of shows up in any old equation you want. Obviously, Austin, it should be clear to you why big G is there, right? Suppose I asked you that question, Austin. Why is big G in the formula?
Big G would be the gravity.
Yeah, you need to account for the effects of gravity, and that's right. Okay. I was going to have us do a sample problem, but we're going to be doing a badass homework today that involves this formula, right? So maybe you guys would just like to take a little kids break, and then we'll at 1 o'clock we'll start the homework for reals. Everyone like that idea? Okay. So we got to where we need to go. A little after 1, we'll start the homework. Take a moment to relax, okay? Don't let me forget to start the recording as well. Okay, Astronomy 1020, it's time for homework number 3. Get your name, Astronomy 1020, and your section. Please write homework number 3 on the page, and let's write down the numbers that we're going to be doing from chapter 4. You guys can find the questions in the homework tab on Blackboard. Here's homework and homework 3. All right, so we have number 45, number 47, number 56. We're going to do 57 DEF. And 58 is actually on escape velocity. I didn't quite get to that, but we're going to do A, C, D. So let's write those down. You guys can find the questions here if you need them. Okay. Stacy, you done to kick things off?
Sure. 45, the gravitational law. A, how does quadrupling the distance between two objects affect the gravitational force between them?
Okay. So we've got the gravitational law to consider. Let's write it down in the manner that Newton wrote it down in his Principia Mathematica. The force of gravity is proportional to the product of the two masses and inversely proportional to the square of the distance. In part A, Stacy tells us we're taking a distance and we're quadrupling it, which means the distance is now 4 times greater. Our job, students, is to find out by what factor the force will vary. Does anyone know how to do this? Before I show you how to do it, I want to see if you guys remember enough to do it on your own. Does anyone know what the answer is? No. I don't know if you guys remember, but well, Austin, it is exponential because it's inversely proportional to the square of the distance. And therefore, you have an exponent. So it is exponential. Not 27. Where'd you get 27 from? Okay. So I gave you a quick example of this in class on Tuesday, and now we're going to learn how to do it right. You'll notice that in part A, we are varying the distance, but we are not varying the masses. Oh. Well, hold on, Austin. Let's fix this, okay? But where are you getting the, yeah, I know that 3 cubed is 27, but where's the 3 come into play? I don't see any 3s here. Also, why are you hiding? Why are you a troll? Talk to me. Okay, listen. Let me show you guys how to do this, all right? What we do is we ignore the terms or the factors that are not varying, and we only keep the factors that are varying. Since we're varying the distance, we write force is proportional to 1 over the distance squared. Now we make another proportionality sign because we're not actually plugging in a distance, we're plugging in the factor by which the distance varies. If the distance varies by a factor of 4 times, I can do 1 divided by 4 squared. Now it becomes an equal sign. What's the answer? What is this? (1/16). What is the meaning of 1/16? Do you guys know what the significance of the 1/16 is?
4 cubed, oh, not cubed, sorry. 4 squared is 16, right?
Right. So now that we've gotten the 1/16, what does that imply about the force? Let me cue you up and then you fill in the blank. if the distance between two objects is 4 times greater, then the force between two objects blank.
Is it 16 times greater?
Not 16 times greater. It's not 16, it's 1 over 16. So rephrase your, was that a Runsack? Who was that?
No, that was
Oh, Wyatt, sorry. Wyatt, so not 16 times greater. Remember, gravity gets weaker with increasing distance, right?
so it'd be 1/16 of 4.
Not
of,
one.
of okay, so
Okay,
the entire
so-
the entire force of gravity is 1/16 of what
That's
it would
it.
be.
So, Caitlin, you wouldn't say 1/16 greater, because as any good banker knows, 1/16 is a reduction, right? If you have, you wouldn't say, why is my bank account 1/16 greater than it was yesterday? That would actually imply that you've lost money, right? So, okay, but that's all right. We're learning how to do the talk here, okay? So the new force, write this down, is 1/16 the old force. Or in other words, the new force is 16 times weaker than the old force. So the new force is 16 times weaker. That's part A. That's all we had to do. Take a second, and then we're going to do part B. May I erase? I'm going to erase. Stacy, part B.
Suppose the sun were somehow replaced by a star with twice as much mass. What would happen to the gravitational force between Earth and the sun?
Stacy, how should our proportionality look this time? If we're doing it the same way we did it last time, I would write force is proportional to what?
I need some help, honestly.
Okay. Well, knowing how to set this up is part of the game here. So, does anyone know what to do? What am I
I do.
doing?
So you have to set the same thing up that you did before. However, it'd be 1/2 squared.
No. I am
Oh,
not
okay.
varying the distance. In this situation, we're not changing the distance. In part A, we changed the distance, but not the masses. So you saw me ignore the masses. Now the distance is staying the same, but I'm changing one of the masses. So I would write force is proportional to,
Oh, so
Would it
then it
be-
would be m1 times m2 over 1.
well, I'm not varying both masses. I'm only varying one of the masses.
Well, then whichever mass that you want to vary.
Yeah, exactly. So force is proportional to, say, m1, or just any of the masses, right? And now, if I vary the mass by a factor of 2, because they are directly proportional to one another, with no cubes or squares or weirdness, force is proportional to mass. If the mass doubles, then
The
what?
force double.
The force doubles, that's right. So the new force is 2 times stronger. That's it. Okay, Stacy, we'll take, I'm erasing. That shouldn't have taken very long to write down. Stacy, part C.
Suppose Earth were moved to 1/3 of its current distance from the sun. What would happen to the gravitational force between Earth and the sun?
So Austin, it sounds like you kind of understand how to set these things up now. What would I write for my proportionality argument? I would write force Let's write it
It's
symbolically first. Force.
1 over d2.
I'm sorry, one more time.
1 over d2.
1 over distance squared.
Yeah.
1 over the distance squared.
And
Okay.
which is also proportional to 1 over 1/3. Can you do that?
What about the square?
Well, squared.
Okay.
1 over 1/3 squared. So like 0.3 squared.
Kind of, but let's keep it as whole fractions.
Okay.
Now, watch
So
what I
then,
do, Austin. This is very important. I substitute the entire 1/3 in for d, and that is squared.
right, which is 1/9.
Right? So if I distribute the square, that becomes 1 over 1/9. So
The
What do
new
I call-
force is 9 times weaker?
wait, weaker?
No, stronger.
Yes, because 1 over 1/9 is 9. So the new force is 9 times stronger than the old force. And that's it. That's number 45. This looks deceptively easy. My friends, you're here to learn something. This proportionality symbol is a powerful operator that can quickly let you solve problems and see the relationships between variables. Professional scientists use this all the time to quickly analyze how formulae work. And you can do things with it, but you're just taking your very first step into this world. As we go forward in our class, I will show you examples of how you can use the proportionality symbol. That problem was easy. The rest of the problems, maybe not so much. I need to erase. Does anyone need another second here? Talk to me, people. Okay. Chapter 4, number 47. Caitlin, you're next to my little Hollywood squares. Would you be willing to read that for us?
Let me unmute myself.
I don't know if I'm taxing the bank here or what.
No. All right, 47.
Yep.
Head to foot tides. You and Earth attract each other gravitationally, so you should also be a subject to a tidal force resulting from the difference between the gravitational attraction felt by your feet and felt by your head, at least when you are standing. Explain why you can't feel this tidal force.
Why can I not feel a tidal force? Could you guys, as part of your answer, I want you to draw a picture with me. I've got a Frisbee. You could use a quarter or some kind of a circle maker nearby. Let's draw the Earth. And make a dot for the center of the Earth. I'll remind you guys that the radius of Earth is 6,400 kilometers. Let's put a man standing on top of Earth.
So are you also a owner under this account?
What's the typical height of a man in metric units? Do you guys remember your first lab where I measured myself? How tall was I? You probably don't remember
Right,
that.
so we're sending to that account, if that account is co-owned, that would have to be.
2 meters, Austin is correct. The average height of a man, when people just want to round it to 1 sig fig, is 2 meters. Now, I am almost not quite 6 feet tall, as some of my ex-girlfriends like to point out. You're only 5'11", okay? But you can see that I'm close enough. I'm closer to 2 meters tall than I am to 1 meter tall. So sometimes people say that the typical height of a man is 2 meters, all right?
Okay, so in Zell, you're
Now,
working to
Caitlin,
a person.
they ask us, why does a man not feel a tidal force from Earth? Before I try to give you my take on it, do you know what the answer is, or does anyone out there have a simple answer to this question?
Nope, I don't have an answer for you. I'm sorry.
That's okay. Let's just ask the hive mind here. How about all of my trolls in the background?
Is it because we're too small?
Too small in comparison to what?
I guess celestial bodies in general, but in this case, the sun, because the sun is what, or the moon, what's causing our tidal forces. Or
That's
so it's
who,
planet.
who was I just talking to? Was that Wyatt?
Yeah.
Yeah, Austin's a little closer. I was worried, Wyatt, that as soon as you heard tides, everyone was going to think the moon. But the moon is not the only body that can exert tidal forces. In this case, they're not considering the moon at all. They're actually considering the gravity of Earth acting on the man. And
Okay.
here, because you said that, I think we need to enhance this picture a little bit. Let's draw the tidal forces that they're talking about. I'm going to do them with some fancy colors. At my feet, I have one force of gravity. This is the force of gravity that the Earth exerts on my feet, which I will call F sub foot. Technically speaking, the feet of the man are a little bit closer to the center of Earth than the head of the man. So there's another force being exerted on the man up near the top of his head. This I will call F sub head. The idea is that the Earth as an extended body acts on a man who is not a point particle. The man has physical dimensions, a length, so that the tidal force, the delta force, would be the difference between the force on the man's feet minus the force on the man's head. It doesn't have anything to do with the moon at all. It's just the Earth's tidal influence on a man. The question then is, why do we not notice these tidal forces? You know what Neil deGrasse Tyson calls this? He calls it spaghettification. When objects fall into a black hole, they can sometimes experience immense tidal forces that will stretch them and pull them apart atom by atom. Why don't we notice the spaghettification that Earth is exerting on us? Austin says it's too weak. Okay, but we need to flush this out into a sentence. We are strong. Actually, you're not wrong. No, it's not about mass, Kevin. When you say we are too strong, I wonder, Austin, what you really mean. What is strong? Here's a thought.
I would say it's like because we're used to it.
Well, you know, there is a certain sense in which you're correct with that. I listened to an interview with a woman who had spent time in the International Space Station. I forget which astronaut it was, maybe Stacy, oh gosh. I'm blanking on her name, but she had this cool thing to say where she was like, when I came back down to Earth and I was standing on the ground, I was so conscious of the force of gravity for the first time in my life. I'm like, it felt so oppressive after spending months just floating free in the microgravity of the International Space Station. Suddenly she was aware of these compressional forces smushing us down to Earth. And she said, I can't believe that humans struggle against this force and live with it all the time. It feels so oppressive. I can only imagine after experiencing weightlessness for months and months, when you come back to Earth, you were totally conscious of the fact that you are stuck to this damn rock, you know? So I think someone saying we're used to it is actually a valid point. As an astronaut would certainly say that. But here we're not just talking about being used to the gravity force. We're talking about the differential force, the stretching apart.
Could this relate to how we were talking about Mars's moon? Because they're at the point where the tidal forces are about to pull them apart because of their size. And we're a lot smaller compared to the tidal forces that are acting upon us. So is that causing us to be a bit stronger in comparison to it?
Yeah, and that's a good way to say it. In fact, could we compare these with apples to apples? Let's convert the radius of Earth to meters. Can anyone do that? Wyatt, can you do that? How many meters is that?
640 million.
Not 640 million. Here, let's do this right. So give me some units.
It would be 1,000 meters on the top, and
Fine.
then 1 kilometer on the bottom.
Okay. Now let's see if we can do this. 6.4. What's my power of 10? No calculator required.
To the 5th.
There are 5 zeros, but you have to treat the 4 like a 0 too, right?
So 6, yeah.
So how do I say that again?
6.4 times 10 to the 6th meters.
Right, but 10 to the 6 is?
Million.
So
So 6.4 million meters.
6.4 million meters. Okay, cool. So that means, let's call this 6 million for the hell of it. Basically, the Earth is 3 million times bigger in radius than the height of a man. The man is millions of times smaller. But so you guys already kind of answered the question correctly through little bits and pieces, but I just want to ask one last thing. What is resisting the tidal force? Like Austin said, we're too strong, but what is it that's strong? What resists why doesn't gravity just crush your ass like a tin can and turn you into a pile of atoms? What is fighting against gravity? Like in terms of
beyond our bones, like
I am talking about your bones, but what
the forces that separate atoms,
the intermolecular forces between atoms, right?
Yeah.
So
yes.
So it's those bonds between atoms. So ultimately, that's what force, not anti-gravity. Well, it's fighting gravity, but what fundamental force is that which governs the separations between atoms and molecules? You remember your 4 fundamental forces, right?
I'm trying to figure. Is that the strong force?
Nope. The strong force binds nuclei together.
Oh, okay.
Anything that has to do with between atoms, they're ultimately bound by their shared electrons. So it's the electromagnetic force. What fights against gravity? The electromagnetic forces that make up your bones are, the number is too stupid to say, it's kabillions of times greater than the force of gravity. In a later point in this class, we'll actually directly compare gravity versus electromagnetism. And I think it's something like 10 to the power of 42 times greater for electromagnetism than it is for gravity. Okay, why don't we just write the following bit down and let's answer this question. A human will not feel a tidal force from Earth because the 2-meter height of this human is millions of times smaller than the radius of Earth. Now, we have to add another sentence. We have to prove that we understand what the tidal force is. Yes, it's about the height of a person being small in comparison to Earth's radius, but now we have to explain tidal forces. We have to say, therefore, the difference between the gravity of Earth on our feet and the gravity on our head is essentially, but not quite, zero. Where's my little marble Earth here? I've got a cute little marble Earth somewhere. Here it is. How's that kitty, Caroline? Is it a happy kitty?
Yeah, she doesn't want to write the stuff right now.
Pardon me? Oh, the cat's
Come
writing
on,
your
right.
answers?
What are you doing? Yeah.
You have to get one of those ink pads and then put her paw in the ink pad and then have her stamp your homework.
I will definitely do that.
Earlier, while you guys are writing, let me entertain you for infotain you. A Runsack, I think, or someone asked about black holes. You know what's so cool about black holes is, technically speaking, black holes are when you compress gravity into a microscopic point of 0 dimensions. Sometimes it's fun to imagine what would happen if Earth collapsed into a black hole. We'll do a calculation later that shows if you collapsed Earth into a black hole, the event horizon of Earth would be about 1 centimeter. So basically the boundary of the black hole would be about the size of this marble Earth here, but it would contain all of the mass of Earth. In fact, however, for a black hole, all of the mass is contained somehow in a microscopic point. Microscope isn't even the right word. It is a mathematical point of 0 dimensions. And that sounds pretty freaking crazy. If Earth were a black hole, even though the mass of Earth is the same, the tidal forces on a man would become insane, because 2 meters is a millionth of the radius of Earth. But if you compare 2 meters or any size at all to 0 meters, you know that 2 divided by 0 is infinity. The length of a man is infinitely larger than the 0-dimensional black hole. And what that means is, as an observer approaches a black hole, the tidal forces also go to infinity, so much so that if you were to fall into a black hole, the tidal forces would actually pull you apart atom by atom. They would exceed the intermolecular forces of electromagnetism, and you would basically be ripped apart into a puddle of plasma. That is fun.
You forgot to mention the cool fact that the speed at how fast you're moving at that point. Because when you actually hit the, I guess, in quotations, surface of the black hole, you're moving so fast that it's like 100 atomic explosions.
Well, we are going to, believe it or not, one of my favorite parts of this course, and you guys are lucky that you're taking it in fall because we have a little extra time. I'm going to give you guys an entire lecture on special relativity and general relativity, which are 2 of my favorite subjects in all of physics. So we will talk about the velocities and those things at a later point in time. But for now, I'll just say one last, the event horizon, yeah. As you know from the fact that we've recently imaged black holes are frequently surrounded by something called an accretion disk. And I'd like to just show you a little artist illustration of one here. Frequently, black holes are surrounded by a disk of hot plasma. And what the hot plasma is at some point, stars probably wandered a little too close to the event horizon of this black hole, and the tidal forces were so immense that they basically ripped the entire star apart and smushed it out into a smear of hot hydrogen plasma. So this gas that you see surrounding black holes is literally chewed up stars that the black hole is ripped apart. So tidal forces, one of the reasons we study them is they may not be strong for Earth or even our own sun, but once you get around tiny objects that have a lot of mass, like these black holes, tidal forces can get real nutty and have these kind of cool effects. Okay, did everyone have a chance to get all this down before I erase it? Caroline needs a second, sure. Yeah, Kevin, if you're an outside observer watching someone hit the event horizon, time runs at a different rate for you than it does for the observer. While the observer passes through the event horizon, an outside observer would actually see time come to a halt at the event horizon. So people kind of stick to the outer event horizon of black holes like flies to flypaper. Oh my God, don't get me started on Interstellar. I have a thing about, all right, Interstellar was, I didn't like it, okay? And I've got some reasons. First of all, they call the, I shouldn't do this right now. Look, they call the movie Interstellar, but the first thing that happens is a black hole opens up outside Saturn and they travel to another galaxy. And I'm just like, wait a minute, what? Why are you going to, why isn't it called Intergalactic? That was my first complaint with the movie. The second one was, it turns out that the wormhole they go through is a type of black hole. You know what? Ask me, I'll tell you what, if you remember to ask me, when we get to relativity and black holes, ask me for my riff on Interstellar and I will go nuts on you. But I'll save it until then so I don't abuse your hospitality here. Hey, Caroline, are you done with this? Okay. I'm erasing. Let's see. Christopher, are you willing to read us the next problem? Number 56. Hold on, I'm having some focus issues here. I need to open up my Logitech settings. Logitech. All right. The 56 looks a little blurry. I wanted to see if I could fix that. Come on, this thing takes forever. Christopher, get ready to read 56 to us. Okay, hold on, guys. I want to try adjusting the autofocus and see if, all right, there we go. That's worse. All right, I think, all right, Christopher, go ahead and read that out for me if you can.
Okay. Understanding Newton's version of Kepler's third law.
Otherwise known as NK3.
Find the orbital period for the planet in each case. Hint, the calculations for this problem are so simple that you will not need a calculator.
Yeah, that's a lie. That's not true at all. Okay, so let's write down Newton's version of Kepler's third law together. P squared is equal to 4 pi squared a cubed over g times the sum of the two masses. And Christopher, once you've written that down, actually, I'm gonna explicitly put the times in there. 4 times pi squared times a cubed. Christopher, once you've got that written down, read me what it says for part A.
A planet with twice Earth's mass orbiting at a distance of 1 AU from a star with the same mass as the Sun.
I want you guys to watch how I write all this down. Two times the mass of Earth, a distance of 1 AU, and the same mass as the sun. So 1 times the mass of the sun. Notice I've used those symbols there for mass of sun and mass of Earth. You should practice doing that as well. Okay, let's just see where you guys are at. Do you know how to start this? Let me get on my tiny stool so I'm not blocking the camera here. How should I begin this problem? Ooh, is Austin joining the party? What do I do, guys? No, he's not joining the party. Okay. Too much Tallulahs for you, huh? Hey, can I just plug all these numbers in or what? Is it just that simple? No. Arunsak, do you know why? What should I do?
I think you're supposed to have the distance in meters, right?
What about the masses?
I don't know about the masses.
We need MKS units, right? What does that mean? I need to know that you guys can understand me. Kilograms, says Austin. Correct. Okay, so let me help out here. The mass of the sun is 2 times 10 to the 30 kilograms. I'll keep my units in red for this problem. The mass of Earth is 6 times 10 to the 24 kilograms. Now it's your turn. What is 1 AU? I can move as fast as you guys can move. What is 1 AU in some other unit? Anyone? Help me. Shoot, I'm gonna need another red marker. Oh, here we go. Come on, guys. I can't do it all for you. You gotta help me a little bit. I need
Isn't
1
like
AU.
doesn't it transfer into 150 million kilometers, right?
Oh, that's right. So now we got to get that into meters, right?
Yep.
So what do I do?
So then use the X bar.
I'm sorry, can you say that one more time?
Do the X bar.
Yep, the division bar.
Yep. Then you got km at the bottom and meters on top.
Yep. Now I get my conversion factor.
It's 1,001, 1,000 up top.
Cool. And can you get that right into scientific notation for the answer?
It's 150, 10 to the 9th.
Right. 150 billion meters. At some point, guys, I might let you just say 150 billion meters is an AU, but it kind of depends on whether or not some of you can remember that. I bet a few of you can. Okay, we've got all of our givens into MKS units. It's time to plug it into the formula here. I'm gonna need a little bit of real estate to do this. So everyone finish copying down. I need to erase. Stacy, let me know when you're good to go. All right, I'm erasing then. All right, can I tell you how we're gonna do this? We're gonna take the square root and put it on, I'm sorry, we're gonna take the square and we're gonna put it on the other side of the equation so that we solve directly for P. So I'm gonna write down P is equal to, now watch my methods here. I'm gonna have a big fat square root because I've gotta put a lot of stuff in it. Don't give me no sloppy square roots. Make a big fat square root. Put your division bar cleanly inside of it. At the top, we will have 4 times pi squared times. Now open your parentheses. our distance is 150 billion meters, close parentheses, cube. We're not going to need to use parentheses in our calculator if we're using the Casio, but the parentheses are there to remind us that not only is the 150 billion to be cubed, but the meters must be cubed as well. So those parentheses are there for the units as well as the number. On the bottom, we'll put big G, 7 times 10 to the negative 11. And the horrible units of big G are meters cubed per kilogram per second squared. Oof. Times, open parentheses. Actually, guys, I want to stop here. Sometimes instead of dealing with M1 plus M2, because it can get a little bit messy, sometimes it's customary to replace M1 and M2 with something called the total mass. And I want to have like a little side quest here, a little mini game, if you will. I want you guys to take a moment and just analyze the total mass of the system. M total is the mass of the sun plus twice the mass of Earth. And I want to write that out, okay? So the mass of the sun is 2 times 10 to the 30 kilograms. The blue comes out a little better for units, so I might switch over to blue. Plus 2 times 6 times 10 to the 24 kilograms. Could you guys do me a solid and could you add those two up for me with your calculators? Let's calculate the total mass first. Maybe. Yeah. So punch that into your calculator. You know how to do that, right? I'm really worried about, oh yeah. Wait, I think you forgot to multiply the mass of Earth times 2, Austin. I'm really worried about, Austin, I'm glad you're punching. I'm worried about the rest of you trolls hiding in the background. You really need to make sure that you're punching this stuff into your calculator or you are gonna eat pavement when the exam comes up. So the people that I can see like Caroline and Christopher and Caitlin and Stacy, you guys are cool because I can see what's going on. And at least Wyatt and Emily and Austin talk to me from time to time. And so does Kevin. But the rest of you guys like Blair, who the hell are you? Tiffany, I don't know. Xavier, I don't even know who you guys are. Like, you're just a little square in a sea of black squares. So if you're not punching this stuff into your calculator, I want to tell you right now, you're doing it wrong and you are going to feel some pain, all right? And I don't want to be too harsh. Life is going to be harsh enough on you as it is. Just please make sure that it's okay, Blair, if you're a troll and you want to hide in the shadows. I get paid the same either way. I'm just scared that a couple of you might be just kind of like passed out, hungover in bed with the bag of potato chips and just not be punching into your calculator. That would be a bad thing, okay? So please be punching, Blair. Okay, what did you get, Austin, or whoever, when you punch this stuff in? Austin, you told us, right? Is it in the chat thing there? Okay, who's Blair? Sorry. 2.0. All right. So if we round this to like 1 sig figure, what should I write down? Round it
2 times 10 to the 30.
Okay, fine. But here's the issue. Isn't that just the mass of the sun? Christopher, is that okay? Christopher, I thought we were supposed to add the mass of the Earth. How can the mass of the sun plus twice the mass of Earth be equal to the mass of the sun?
Because the sun is big.
Well, more massive, you mean, right?
Yeah.
Big implies size. Well, the sun is big too. But in other words, Christopher, it sounds like you understand. The Earth is insignificant. Even twice the mass of Earth hardly matters. Yes, Reardon said the Earth is too small or too low mass to really make a difference. Once again, Reardon, the gravity formula cares about mass, not size. So in other words, this is a trick that you have to know to play sometimes. We can often neglect one of the masses. You're going to see me do this a lot. We can neglect one of the masses if they're exceptionally tiny. And that greatly simplifies the formula because then the total mass just becomes the mass of the sun. I need to point this out to you guys because many problems depend upon that trick. And if I didn't show you that trick, you might not have known to do it. So we're going to erase these parentheses. And in here, we're just going to put the mass of the sun. 2 times 10 to the 30 kilograms. The punching of this into your calculator is going to be a little intense the first time around. So I'm going to walk you guys through the plan, all right? If you're not using a Casio, then you're on your own. But first, we're going to talk about the strategy, and then we're going to do it together. Okay, watch this. Yeah, Devin. Well, Devin, I'm going to explain that. Remind me at the end of this problem to explain that. 4 times pi squared, we're going to do this. We're not going to use parentheses. We're going to do 150 exp 9 cube. We're going to divide by g. Then this is the key part. When we get here, we're going to divide by the mass of the sun. Then we're going to hit equals, and then we're going to square root it. Y'all ready to go? This is going to be a bit of a trip, okay? I'll try to do it so you can see my calculator and the formula. Okay, 4 times pi, square that, times. Sorry, Stacy, I couldn't hear that. Now we're going to do 150 exp9. Remember that your cube is here. Shift cube. Divide by g. 7 exp negative 11. And then we're going to divide by, even though it says times, divide by 2 exp 30. And then we're going to hit equals. And now we're going to square root the whole thing. Shift square root. Show me what you got. Show me your calcies. Hold on. I'm going to go to speaker view here. Caroline, keep that up there. Wait, can you show me again? Caroline, you're a little too close. Back up. Oh, it's too dark in your room. You lost power. Get up in the sunlight. Anyone else have it for me? Emily, what do you, hey, Tiffany, that looks awesome. Good, Tiffany. I like it. Anyone else? Yes, that's good, Caroline. How about Emily? You got something for me, bud? I can't hear you, but yeah. Whoa. Oh, no, something went wrong, Emily. Emily, we got to do that again together, but let me just check out everyone else out. Stacy, Kate, how are you guys doing? Did you get lost? All right. Chris, what do you got? Chris, let me zoom in on you. Hold on. Yes, that looks good, Chris. Nicely done. Well, Devin, that's what we're doing here. I specialize in Wyatt. Let me zoom in on you for a sec, buddy. Hold on. Full speaker view. Hold on, Wyatt. Don't move. I gotta find you. Don't move. Where the hell is? Oh, here he is. Yeah. Wait. Wyatt, is there a decimal? Can you back it up a little bit? Is there a decimal point there? Hold on. Hold that up again, buddy. Sorry.
A decimal point where?
1, 2, 3, 4, 5, 6, 7, 8. Something went wrong, dude. Something went mad wrong. Your calculator's a little different, so that's probably okay. Caitlin, oh no, no good. Okay, can I tell you what? This is where I always do this the first time around. I love doing it in person because I can walk around to everybody's table, and you know what I end up having to do? I end up having to just punch it with every single person. There's too many of you for that, so you're going to have to kind of watch me again, and I'm going to do it slower, okay? Slower and better. And I'm going to adjust my focus. Let me see if I can adjust my focus at this calculator so I can get real close. Hold on a second. Yeah, there's my autofocus. I think if I go to a, oop, that's my zoom. If I go to a focus of like 38, yeah, that's nice and sharp now. Okay. So let's do this together. Keep in mind I'm working backwards, so I might be a little awkward here. Everyone punch after me. 4 times pi squared times 150 exp9. Now I got to hit my cube here. Shift cube. Let's divide by g. Divided by 7 exp negative 11 divided by mass of the sun, 2 exp 30. Then I hit equals. I should see something times 10 to the 14th. Now I've got a square root. Shift square root. I'm sweating. Sweating to the math here. Emily, yeah, you go, girl. You got it. Caroline still looks good. Hold on. I got to hide the trolls here so I can see. There's too many trolls. Video settings, hide non-video participants. Okay. Who else is out there? Yeah, Wyatt, that looks good. Wait, Wyatt, can I tell you why I'm screwed up here? I don't see a decimal point. Is there a decimal point in there somewhere?
Yeah, so I looked at it and then I looked at yours. So it is right, but I don't know
But
why
it
you
just-
can't see the decimal point.
It,
I mean, like 3.084.
Yeah, but do you have, is it that the decimal point is there, but I can't see it through the camera, or is the decimal point
I
not
think
there?
so. I think it's just through the camera because I can't really see yours either.
Oh, you can't see my decimal point? Wait,
Not really.
hold on. Let me go to me for a second. Because I'm in
It's
focus
after
now.
the 3, right?
On my camera, the decimal point looks clear. Stacy, what'd you get? Can I
Oh
see
wait,
yours?
where is the decimal point for you?
Can you
Is
not
it
see
after
my?
the 7?
Yeah.
Okay, I think. Hold on, mine's after the 3, so I'm gonna see what I
But
figure or what I
I don't
get.
see any scientific notation on yours. Hey, I hate to say this, Wyatt, but this is one of the reasons why everyone needs the same calculator. Because
Calculator.
I'm going to end up giving separate instructions. Hey, Caitlin, did you get it? Caitlin, you were having troubles before. Stacy, that's good. Yeah, Caitlin, that's good. He's got a slightly different, he's got like the FX300 or something. Or is it the 310 or what is that, Wyatt, that you have?
Why
I
don't
think
you explain to everybody what calculator you have?
Okay, Slacken. Yeah, right, Gianna. Hey, you know what? I kind of like Wyatt because he always has really good comments. Okay, so Wyatt, I'm going to break the rules for you this way. Hey, get your video back over here, young man. Okay, I'm going to break the rules for you one time, but this might help other people too. Wyatt, you have what's called a line entry calculator. And the genius of your line entry calculator is that you can plug the whole thing, square root and all, in the beginning. So here's a separate set of instructions for you, you little snowflake, okay? I want you to do a square root. Then I want you to open parentheses. I used to have one of these calculators around here. So Wyatt, do a square root. Sorry, I do have, where the hell did I put that thing? I think my, My TI-85 is dead. All right, look, square root, open parentheses, make sure you do 4 times pi squared times, oh, by the way, can I see your EXP key? Show me your EXP key, Wyatt. That could be what's going on. Oh, no, okay. All right, so do 150 EXP9 qubit, divide by G, divide by the mass of the sun, then close parentheses and hit equals. Your numbers, your string of numbers looks good. It's just that if you say the decimal point is after the 3, I'm expecting to see a little exponent for scientific notation. I'll tell you
Usually
what.
there is.
All right, I'm approaching this all wrong. What's the answer? Let's just get down to business. What's the bloody answer?
It was like 3.1,
3.1, but Kevin, not just 3.1, right? You're missing something. No, Kevin. No, no, no.
3.1 million.
Not 3.1 million, Christopher. Count the spaces better. Million is 10 to the 6.
It's to the 7th, right?
Yeah, who said that? Who's that?
Daniel.
Daniel, you rule. 3.1 times 10 to the 7. What are my units, Daniel? Daniel, you're going to unit jail. What can I cancel here?
Would it be meters to the second?
No, because you have a meters cubed here, but that cube.
Oh,
also,
right.
So meters actually cancel. What else cancels?
kg.
So what do you have left over?
S squared.
No. You have the square root of 1 over seconds squared. That's what you have. You don't have s squared. You have the square root of 1 over seconds squared. What does that reduce to? Anyone? Did I lose you, Gianna? Say yes or no. All right. Gianna, I want to do that once more because what I just did there is kind of an important skill. So let me do this for Gianna, and I bet a few others will benefit from it. Gianna, let me know when I lose you. Meters cubed is the top of the bottom. Meters cubed is the top. Meters cubed and meters cubed cancel. All right, so you're good with that. This is a division bar. This is kilograms on the top of the bottom. This is kilograms on the bottom of the bottom. Top and bottom cancel. Your kilograms are gone. Now you have the top, which is a 1. You have the top of the bottom, which is a 1. And seconds are in the denominator of the denominator, but they're seconds squared. And there's a square root over all of this. Now, as you learned the other day, the bottom of the, Caitlin's shaking her head. Come on, if you can do bank stuff, you can do this. 1 over seconds squared reduces to the square root of seconds squared. And my final units are?
So just seconds, right?
Yeah. Which is obvious because it's a unit of time and we're in MKS system. Gianna, I hope you followed that a little better. You probably got mixed up. Okay, the computer does. Yeah, but here's the deal, Caitlin. Which end of the computer do you want to be on? Do you want to be the droid punching in the buttons, or do you want to be the person who's making the code? That's what it's all about, you see? That's when they pay you big bucks. And you know, can I tell you something, guys? I hated learning to program computers when I was in college and grad school. I resisted it. I fought it. I was a brat. And then I got my first job out of grad school and I was programming computers and it was so much fun. Nobody had any idea what I was doing. They couldn't check my work. And it was like a little puzzle that I had to solve every day. It was so much fun. So Caitlin, yeah, the computer does 90% of the work for 90% of the people. The goal is to be the 10%, to be the people who are pulling the levers, all right? Anyways, enough of that. Well, then you have to get some brain power. Now listen, we cannot leave the answer in this form. I want to convert this to a unit that we can understand. This is 31 million seconds. Let's convert it to years. Caitlin, you're up, okay? Dimensional analysis with me here. Show me that you can program the computer. Help me convert that to years using dimensional analysis.
I believe that
Oh, dimensional analysis. Very fun. I'm gonna go back to this 1 second.
Get your steps ready to go.
That was like the first thing that we learned, wasn't it?
Yes, and it's got 3 big stars next to it, so you can't miss it.
Oh, yeah. Okay, so
Step 1.
so we have to step 1. God, my notes are terrible. Okay, yeah. So lesson 1, you have to count the number of stars. Or not
No.
stars.
Forget about that.
No.
You're looking for the 4
Oh.
steps of dimensional analysis.
4 steps.
It's a page after that.
A page after that. Okay. I'm sorry. 1 second. Got a bunch of holes in my notebook from that lab too.
Uh-oh. 4 steps of dimensional analysis.
Oh, here we go. Okay. So write in the number to convert with its units.
So what do I write?
We're doing this for that 3.1 10 to the 7, right?
Fine. So we write down 3.1 times 10 to the 7 seconds. What's step 2?
Multiply by a division bar.
Okay.
And then put in the units first to cancel. So put S on the bottom. And we're converting it into years.
Yep.
So put years on top.
Okay, listen. We can only do this if you guys know the number of seconds in a year. If you don't know that, then you're going to have to do it the long way. It's up to you. I had you work out the number of seconds in a year in one of our lectures, but I'm guessing most of you don't remember it.
No, I think it's on this page.
No, Devin. Oh, Austin. How did you know that, Austin?
3.15 times 10 to the 7 seconds.
Good. It's pi times 10 to the 7 seconds per year. So since, well, who knew that? Was that you, Caitlin, or was that someone else?
Yeah, it was in my notes.
Oh, cool. All right. So where do I tell me what numbers to put where?
Okay, so you want to put 3.15 times 10 to the 7th on the bottom.
Yep.
And then 1 on top.
Good. All right, so punch them up and what do you get?
Okay, 1 second.
I mean, they're almost the same number, right?
Yeah. Don't make fun of me. I'm bad at math.
But if you'd like, I can also answer that for you.
That's right, Devin. I knew that.
That was seconds in a day?
Well,
we
needed the seconds in a year. He gave, no, you did good, Caitlin. I was just talking to the chat.
Sorry, I was confused.
Yep.
Okay, so 315 million?
No.
Thousand.
No.
I don't know.
Austin's got it.
31,500. I'm so sorry.
Look, it's 3.1 times 10 to the 7 over 3.1 times 10 to the 7. It's approximately 1 year.
What?
Yeah. Or in other words, wait, why are you saying what? Here. You punched it bad. Watch.
Of course I did.
All right, well, that's okay. We're going to learn how to do it. 3.1 EXP7 divided by 3.
Divided by.
Yeah, it's in the bottom, right? EXP7.
I read the X and I put it multiply. That's why. Okay, I get it now.
Well, it is multiply. It's multiplied times the division bar. So everything on top you multiply, everything on the bottom you divide, right?
Yeah.
Okay. By the way, box this and put a big duh next to it. Guys, of course the period is 1 year. You've got a distance of 1 AU and you're orbiting the sun. It's going to have the same period as Earth. All of that, like, you should have been able to predict that without having to do all that work. But whatever. Okay. Let's move on to part B now. Christopher? All right, look, we're Here's the problem. Right now, you guys are, well, Gianna, kind of. But Gianna, let's see how we deal with the next one. I need to erase this, guys, so I can pick up our pace. You guys will get a little faster at this, hopefully. I'm erasing. What's part B say, Christopher?
A planet with Earth's mass orbiting at a distance of 1 AU from a star with 4 times the sun's mass.
Okay, so I have 4 times the mass of the sun plus 1 times the mass of Earth. Students, can I make any simplifying assumptions here? How can I simplify this?
Negligible.
I'm sorry, could you say that again, Austin?
The Earth is negligible.
Yeah, the Earth in comparison to 4, because this is an addition, adding the mass of Earth to 4 times the mass of the sun is like adding 3 pennies to Bill Gates's bank account. It's just not going to matter, right? So we can cross out and neglect the mass of the planet. And now we'll put in our values because we have them ready to go. The period will equal the big square root of division bar 4 times pi squared times open parentheses 150 billion meters cubed, that's 1 AU from the last problem, divided by big G, 7 times 10 to the minus 11 meters cubed per kilogram per second squared, times 4 times 2 times 10 to the 30 kilograms. I want to see what you guys remember. You guys punch it up, see if you can do it without my help. And while you're punching, I'll play you a fun song. This is your punching music here. You can find the recording on YouTube or you can find it on Blackboard. It'll take me an hour or 2 to render the video and post it there. Okay, guys, that's it. This is a tough homework, so it's going to take the full 2 hours. Adios. Make sure you finish later and upload this. I want to see that good work. All right, the rest of you guys, did anyone get through the punch out there? Does anyone have an answer for me? Daniel, that might be correct. Wait, why can I not remember now? Yeah, Daniel, you got it. Daniel got 1.5 times 10 to the 7. What are the units, Daniel?
Would it be the same thing?
So, same thing, meaning?
Oh, sorry, seconds.
Correct. Gianna, we'll help with that. I suspect it's not only Gianna who had trouble getting this. This is the correct answer, but let's just stop here and make sure everyone can get that answer with us. So Daniel, you've done good. I'm impressed. Gianna, do you need to see another punch? Okay. Gianna, can I already know what you did wrong. Do you want to know why you got that number, Gianna? You need to hit divide here. Divide by 4, then divide by the mass of the sun. Right. You have to remind the calculator that stuff is in the bottom. So punch it again, this time dividing. Let me talk to the rest of you. Emily, how did you do? Did you get it?
I made the same exact mistake as she did.
Yep, that's very common. So try it again, Emily. Caroline, Stacy, Christopher, Kate? How'd you do, Kate?
I did the same thing she did too.
Okay, yep, I expected that. We got to get out of that habit, so punch again. Christopher, you get it? Okay. Yeah, nicely done. Caroline?
How do you square the
Do you mean square or square
pi?
root? Wait, say
Or
that again?
it's 4 times and then
All right.
pi.
Here, let's do it all together. I'm sure people in the night class will appreciate the extra TLC too. So I imagine if you're in the night class and you're watching this later on. No, Caitlin. All right. Can we all do this together here? Four times pi, square that, times 150 exp9 shift cube, divide by 7 exp negative 11, divide by 4, divide by 2 exp 30, then equals, then shift square root. Yes, Emily. Yes, Caroline. Yes, Stacy. Yes, Ty. Excellent. Kate? Yeah, Ty. Okay, you got it too, Caitlin. All right, cool. All right, so let me do my focus here. How many years is that? One year is 3.15 times 10 to the 7 seconds. How many years? That's right, Austin. I thought you had to go, Austin. Half a year.
Waiting for the answer to this one.
Okay, now I want to really piss you guys off. Gianna wanted to know, why did they say this problem is so simple, you won't need a calculator? The reason they said that is because they thought that you had the same powers that the author does of knowing how to use a proportionality symbol. Let me show you how we could have gotten that answer much simpler. We could have started off by writing the period is proportional to a cube over the total mass. The distance did not change. It's still 1 AU. But the mass is varying by a factor of 4. So p squared is proportional to 1/4, and therefore p is proportional to the square root of 1/4, and the new period is half the old period. You could have done that in one line had you known how to wield the power of the proportionality symbol. But you didn't. And by the way, say that? No, you can't use that. Hell fucking no. Forget about that. That never happened, okay? You have to do this. You're not ready for that. You can't go and fight Darth Vader when you don't even know how to swing on the vine in Dagobah. You gotta have to learn how to do this stuff, okay, before you can pull those kind of maneuvers. But I wanted to show you, my goal was to show you that proportionality symbols are powerful tools that can let you avoid a lot of this nonsense, okay? Okay, let's move on to the next one. Time's ticking here. I'm erasing. I hope you guys are okay with that. All right. 57 DEF. Caroline, can I impose on you to read? By Austin.
Yeah.
While Caroline is queuing up 57, let me start off by saying that in this problem, we are going to rearrange NK3. So this is more work in NK3, but we're going to solve it for the mass of the system. This is one way to write NK3. P squared is equal to 4 pi squared a cubed over g times the total mass of the system, where the total mass is the sum of m1 plus m2. I can do some algebra and flip the total mass up and the period down to get a new formula that's very important. NK3 solved for mass. And it goes like this. The total mass of my orbital system is 4 times pi squared times a cubed over gp squared. Before Caroline reads, Caroline, do you want to take a second to write that down?
Yeah.
I'm sorry?
Yes, please. 1 second.
Yeah. Everyone needs a second to write that down, so you catch up.
Calculate the combined mass of Pluto and its moon. I'm not sure how to say that.
Sharon.
Sharon. From the fact that Sharon orbits Pluto every 6.4 days with a semi-major axis of 19
thousand?
Is a million? Thousand, yeah, 19,700 kilometers.
Okay, let's just make sure you guys can identify the variables. What variable is this and what variable is that? I want to see what you guys know. Oh, my back is starting to hurt. This is back-breaking math here. Emily, what variable does this represent in the equation?
Would it represent the A?
Remember, A is the semi-major axis or the distance. But this is a time, 6.4 days. So try again.
So the 19,700 would be the distance for A.
Correct.
And then the 6.4 would be the P.
That's right. Emily, are these ready to be plugged into the equation, or do I need to do something first?
Wouldn't you have to change them into scientific notation?
It's not about scientific notation. They're not greater than a million, so right now that's not an issue. It's not scientific notation. The issue is, what's the issue? I'm
The
confused.
units?
Yeah, what's wrong with the units? You're so close.
I'm not exactly sure.
Are you blanking? Does anyone else know what I'm talking about? Talk to me, people.
They have to be converted into seconds, right?
This one does. What about this one?
Into just meters?
Into meters. We need MKS. Emily, that sounds like a you job, okay? Emily, will you help me, struggle though it may be, will you help me do dimensional analysis And I'm going to have you convert 6.4 days into seconds. And maybe Christopher can do the meters afterwards. But Emily, help me with the period. So how do I start? You want to get your 4 steps of dimensional analysis, or do you know what to do?
Would it just be 6.4 days times with the division, and then it'd be, we're converting it into seconds?
Yep, cancel your units first.
Cancel.
In other words, I'm trying to give you a hint. If you have days on top, then
Days would be on the bottom,
correct.
and then seconds on the top.
Okay, Emily, you can only do that if you know the number of seconds in a day. Do you know the number of seconds in a day? No. So why don't we go for, Devin does. Okay, Devin, it is true. Maybe you know the musical Rent or something. Devin knows that. I also, Emily, I could have told you it's 86,400 seconds in a day. Yes, Devin, I know that too, but I don't think that's good for Emily right now. I think Emily needs to struggle a little bit, and she'll thank me for it later. Emily, let's say you don't know the number of seconds in a day. Where would you go for, what do you know days into off the top of your head? You know the number of
Hours in a day?
That's right. So let's go to hours first. And in fact, Emily, if you don't mind, let's just set up all of our units. Days will cancel. Then I'll make another division bar. What units go in next?
Minutes?
Right, so hours are on the bottom and minutes on the top. And then what's my last division bar gonna have?
Seconds.
So seconds.
On the top.
Okay, now Emily, help me put in my conversion factors here. I want numbers top and bottom.
Okay, so the first one for the hours would be 24 hours, and then 1 day would be on the bottom.
Correct.
And then 60 minutes in 1 hour.
Correct.
And then 60 seconds in 1 minute.
And Emily, the reason why we're doing it this way is not everyone is going to know the number of seconds in a day when the exam comes. But I know that everyone knows the number of hours in a day and the number of minutes in an hour. So this is how you could convert this under your own power if you ever had to. Okay, punch them up, class, and tell me what the period is. Devin says he gets, Devin, let's just keep it to 3 sig figs, 553,000 seconds. Can someone else confirm that they got that as well? Caroline
Yeah, I got that as well. Yeah, I
okay,
got that
cool.
too.
All right, awesome, Caitlin. Hey, Devin, Mr. I know the number of seconds in a day. Devin, can you help me convert 19,700 kilometers into meters? You can talk to me or you can chat me. I don't care. Just tell me how to do it. All right, Devin, tell me how this works. I'm going to go up top here. Okay, Devin, so what do I do? All right, that sounds right. Devin chats, start with your 19,700 kilometers. Make your division bar, kilometers on the bottom, meters on top. What's my conversion factor? Or I don't know if he lost his internet or what, but doing this through chat is kind of irritating. What's my conversion factor, students? I know you know this. Anyone? Stacy? What's my conversion? Oh, here we go. C.W. Williamson or C. Williamson. Hey, C. Williamson, what's your name? I want to change your, I like to know your first names here. Oh, Cole. Okay, Cole says 1,000 to 1. Kevin says 1,000 to 1. Fine. Okay. That's okay. I can do this. See, hold on a second. Security, no, stop video, video settings, hide non-video participants, and then CW Wilson rename to Cole. All right, cool. Sorry guys. What's my, how should I write this down then? 1,000 to 1, what do you get? Oh, I like Cole's style. Cole is saying, let's make it 19.7 million meters. I would have done the exact same thing, Cole. Nice moves. Okay, let's take a step back and think about where we are. We now know our A in meters. We now have our period in seconds. We are ready to plug it into this bad boy and crunch and punch. I'm going to erase here down, okay? So this is still part D, okay? The combined mass of Pluto and Charon is 4 times pi squared times 19.7 million meters cubed divided by big G, 7 times 10 to the minus 11 meters cubed per kilogram per second squared, times the period, open parentheses, 553,000 seconds squared. It would be a very good exercise for you to try to do this first before I show you how. And that's because many of you are going to screw it up. We want to see if we can do this on our own power, which is where I want you guys to get to. So take a second and punch that while I refresh my ice water. All right, what'd you get? Show me your numbers. Caroline, I'm having a little trouble reading that. Stacy got it right. Caroline, can you, it was, hey, Daniel, you got it right too. Gianna, if you got that, you're killing it. Caroline, what'd you get? Maybe you can just tell me. Tell me or show me, I don't care. Wyatt, that looks pretty good.
I don't think it's right.
Well, what is the right answer? How do you know it's not right if?
I don't know. I got 2.62332.
Times 10 to the something, or? That's kind of important.
Will be.
No, is there a power? Did you get...
to the 24th.
Oh, okay, you're off by a bit.
Yeah.
You're off by a factor of 100. I think you punched the wrong number of zeros in there or something. Emily, that looks good. Caitlin, sorry, kiddo. No good. Caitlin, you forgot to cube your A. That's what you did, or something like that. Wait, hold on, you're muted, so I can't hear you.
That's what happens every time. I don't know how I miss it every single time.
Well, because
Sorry.
you guys are still all brand new. You have to do it again. Blair, 1.3 or 1.3 times 10 to the something. Chris, yeah, it looks like you got it, Chris. Nice. So Caroline and Caitlin, we're going to work on you guys. Let's see. Stacy, how'd you do?
Are we supposed to square root this too or not with this one?
No, Stacy, you got it right. We do not have to square root this because the square root turns back into a square for P. Sorry, Blair, you're off by a little bit. Actually, Blair, I already know what Blair did. Blair, because you hit times there. Blair, you need to hit divide there, not times. That's what you did wrong. Usually, if you tell me your wrong answer, I can tell what you did because I've been doing this for so long. Sorry, I got a spicy pepper in my throat there. Okay. Caitlin, Caroline, try it one more time, and otherwise I got to show you how to do it. In fact, maybe I'll just show you how to do it for the sake of the night class. The night class watching these videos later, hello guys, how are you? If any of them have questions, they won't be able to directly ask them as easily. So let's do it together. 4, oops, clear that. 4 times pi squared times 19.7 exp6 shift cube divided by 7 exp negative 11 divided by 553,000 squared equals. Caroline, Kate, did that come out better for you? Kate, you got it. Caroline, how about you? That looks good, Ty. I like what you're doing, Ty. I like that Ty hid her, presumably herself with the calculator, so I did not actually get to see your face, but that's okay. I know you're here, and I appreciate that. Caroline, how'd you do? I think you just muted yourself, Caroline.
Oh, shit. 1.4?
1.4, yeah, times 10 to what power? Let me give you a hint. Caroline, this is the most important part of the number. It's your power of 10 that matters. Talk to me, Caroline.
Is it times 10 with
To the
22nd?
Yes. In other words, Caroline, let me go to, shoot, I got to focus. I got to adjust my autofocus here. Our final answer is 1.4 times 10 to the 22. What are the units, Caroline?
This is seconds.
No.
Kilogram.
Yes, it's kilograms. This is a mass. Everyone box that up. That's your final answer for D. Okay, I'm just thinking here. How do I want to do this? Screw it. Let's do part E. I can't even remember who was reading. Was it Christopher? You were reading, right? Who was the reader?
I just read D.
Sorry, Caroline. You were. That's right. He was the previous one. Caroline, can you read us 57E?
Calculate the orbital period of a spacecraft in an orbit 300 kilometers above Earth's surface. Sorry, that was cringy.
That's okay. I think everyone should draw a picture of what's going on here, okay? Okay, I'm going to make a command decision here, students. I'm crossing off part F, and I'm crossing off parts C and D. Because we're moving slow, because you guys are kind of, I don't know how else to put it, because you're kind of newbies, you know, because you're noobs. We're going slow, which I expected, but I'm going to cut down on our workload a little bit so we can try to finish on time. So we're going to do this problem and one more, and that's all that's standing between me and the weekend, okay? So let's try part E together. Does anyone object to that, by the way, or would you like to do more work? I don't, no, okay, everyone likes that, yeah, all right. So let's draw a picture, let's draw Earth. And as you know, Earth has a radius of 6,400 kilometers. In this problem, we're dealing with a space shuttle. And the space shuttle is 300 kilometers above the surface of Earth, okay? And it's orbiting around the planet with some period. This is somewhat close to the height of the International Space Station, by the way. Sometimes I do this as a lab. I may do this next week in lab, or I might do something different. Depends on how far we get. You're going to need to know the mass of the Earth. The mass of the Earth is 6 times 10 to the 24 kilograms. The mass of the shuttle is irrelevant. We're going to use Newton's version of Kepler's third law to solve this problem. P is equal to the square root of 4 times pi squared times a cubed over big G times the mass of the Earth. We're neglecting the mass of the shuttle as irrelevant. So we can say that the total mass is the mass of the Earth plus the mass of the shuttle, which is approximately just equal to the mass of the Earth. That's just justifying why I substituted in the mass of the Earth. Students, your question and the real trick to this problem, the reason you need my help is because I bet you most of you will not be able to figure out what the A is. What should the A be in this case? Take a guess. Ah, Devin knows. Devin can see that the shuttle is orbiting not the surface of Earth, but the center of Earth. So that, and this is a trick, students, you got to know this trick. A is the sum of the height plus the radius of Earth. So A is 6,400 kilometers plus 300 kilometers equals 6,700 kilometers. Stacy, can you help me convert that to meters? Because we need MKS units, please.
You hate me. All right. All right, so I'm going to go back.
Deep breath, you got this.
I got this. All right, so you want me to put it into the formula?
Use the 4 steps of dimensional analysis. I'm sorry, maybe I didn't make myself clear. Stacy, I cannot use A in its current form because A is currently in kilometers. This formula is an MKS unit formula. A must be in meters or it breaks. So
Okay.
I need you to help me do dimensional analysis and convert that into meters.
Okay, so it would be 6,700 kilometers.
Yeah, I was about to have a...
I got it.
All right.
Times, and then the bar, and then you put kilometers on the bottom. And then we're trying to convert to meters, so put meters on the top.
Very good.
Thank you. So it would be 1,000 meters on the top and 1 meter on the bottom.
1 kilometer on the bottom.
I'm so sorry, yes.
Can you do this in your head? I bet you could. How many zeros do you have?
I have an airplane going over, sorry.
Oh, it's all right.
Right.
Oh, someone want to chime in there? Look, I don't care how you get it. Yeah, you've got 5, Gianna, but you have to treat the 7 like a 0 too. So I get what? 6.7 times 10 to the what? 6, says Emily. Correct, meters. Okay, good, Gianna. Now, let's plug it in. I'm going to erase up top here. I know you guys are getting the zap. I'm getting it too. We don't have that much more to go here. The period equals the square root of 4 times pi squared times 6.7 million meters cubed divided by big G, 7 times 10 to the minus 11 meters cubed per kilogram per second squared times the mass of Earth. 6 times 10 to the 24 kilograms. There's no doubt about it, guys. This homework is a big learning curve for you guys. This is probably harder than what you're used to, but it'll get easier. It will. Punch and crunch, students. See if you can do it without my help. That's where I want to get. I want to get to a place where I can say, give me the answer. Damn slinky. Yeah. Slinky. Oh, there it is. Meanwhile, while you're punching and crunching, I'll show you guys my magnetic sand. Watch this. Stuff, right? Magnetic sand. Woo, magnetic sand. That shit's crazy. Okay, Stacy. No. What did you do wrong? Did you square root? Did you forget to square root? You did square root, huh? You forgot to cube, Stacy. Or no. Wait. I'm out of focus here because I'm goofing off. Common mistakes are forgetting to cube, forgetting to hit divide, or forgetting to square root at the end. Maybe I just should punch you guys through this, huh?
No, I know what I did wrong. I did something stupid. Don't want to talk about it.
See, that's okay. See if you can get it on your own because you'll be stronger that way. Chris, Caroline, Kate. Beautiful, Caitlin. Beautiful, Caroline. You guys crushed it. Yeah, look at that. Booyah! You're going straight to the top at Bank of America. Here we go. Chris, it's been funny. I've been watching the number of non-video participants slowly decline during the course of this. No. You're good. You're good, Caitlin. It just, you have to do a couple of bad ones first before you get it right. I'm not worried about you guys. I'm worried about all those people in the background who might have lost their energy. I hope that they're going to do the rest of this work and submit it properly later. Otherwise, I'm going to open up a can of whoop ass on these folks. So all of you students out there who are listening later, please get your work in. Chris and Stacy, I'd still like to know that you guys got it. What? Yep. Well, sorry, you got the same thing again. Okay, I'm going to do this. I think the fastest way is if I just do it and show you. Focus 38. All right. Here we go. 4 times pi squared times 6.7 exp6 shift cube divide by 7 exp negative 11 divided by 6 exp 24 then equals then shift square root. I know I did that kind of fast. Chris, can I see you? Chris, it doesn't look like you got it right. Emily, you did get it right. No, look, Stacy and Chris, I want to help you, but how do I help you? Tell me how I can help you.
Can I say it and you tell me where I'm going wrong? Can I do it with you? Because I don't know. Okay. And can I just see the board again? Because I forgot to square the pi. Like, oh, I can read it. It's fine.
Yeah.
It's negative 11. Yes. M3 divided by 6 to the 24th. Okay. All right. Thank you so much. All right. So it's 4 times pi squared.
Correct.
Times 6.7 exp6 shift cubed.
And make sure you're hitting the cube and not the cube root, right?
I hit the shift cube, the little diamond. Yes, okay, good. And then I divide it by 7 exp negative 11
Good.
divided by 6 exp 24. Do I hit equals here?
That's when you hit equals, and then you square
I hit
root.
equals and then shift square root.
And what do you
And
get?
then do I hit equals again?
No, just once.
I got that.
All right, now you got it right.
So what did I do? Oh, whatever.
I don't know, but who cares? You're doing it right now. That's all that
right.
matters.
Thank you so much.
So, Kate, you got it right off the top. What would you round this to, Kate?
I put 5.3 times 10 to the 8th, but I don't think that's right.
But that's not what you got, buddy. Look, you got this.
I tried to
Your
put it in, like, I moved it. I don't know why.
Okay, but wait, hold on, Kate. Look, Kate, your decimal place, hold on. The decimal place, sorry, I've got glare from my windows.
I know where it is. I moved it. I
That's not times 10 to the 8th, though. First of all, this number is a number of order 5,000. You totally do not need scientific notation for that. All of this stuff is garbage.
Okay.
Forget about all of that. No, Stacy. Yeah, Stacy, that's what it says on the calculator. But Stacy, you don't need all that precision. Most of these numbers are junk numbers. Stacy, what should I write?
I was helping Daniel. Okay, I got you. All right, so it would be, wait for it. It would be,
one thing to get the right answer. It's another thing to know how to round it and understand it.
yes. See, that's what I get. All right, so it would be, I want to keep 3 numbers?
2 sig figs.
2 sig, so it would be 53.17.
No, false.
No.
The answer is not 53.
5.32. I'm guessing now, I'm sorry.
Students, I think that you guys confuse rounding and scientific notation. I'm starting to worry that you think those are the same things. They're not the same things. Scientific notation is a way we express numbers when they get too big. I don't think 5,000 is too big of a number for you all to handle. You can handle 5,000. So don't put it in scientific notation, but do round it to 2 sig figs. What's my answer? Too many sig figs, Caitlin. Caitlin, that's the right idea, but why? Yeah, it's like you're a banker. You're on bank. We have to have 2 decimal points all the time, right? No, Caitlin, if you were to write 5300.00, that would be 6 significant figures. To a scientist, if you put the decimal, so I think you understand though, it's 5,300. 5,300, and what are my units? Seconds, says Devin, correctly. How many minutes is that? How many minutes is that?
88.
Yeah. If it's 60 seconds per minute, it's approximately 90 minutes. That's roughly the period of the International Space Station. Okay, thanks to the generosity of your professor, we only have one problem left to do, and it's a problem on escape velocity. I got some good news and some bad news for you. The bad news is that I haven't gotten to this formula in the lecture yet. But the good news is that the formula is much simpler than what you've been doing so far. So it is an MKS formula, but it won't take us too long. Please box up 5,300 seconds and box up 90 minutes. I am going to have to erase here. Stacy, I don't know if you read oh, you did read a problem. Emily, did you read a problem for me, or will you read a problem for me?
Hold on, let me just pull it up real quick.
Yeah. Meanwhile, guys, I want you to set the problem up like this. So this is 58A, our last problem. It's on a formula called escape velocity. The escape velocity from a planet is the speed that you need to leave the planet's gravity. It's the speed a rocket needs to travel at. So draw a planet with a little rocket on it. Show an arrow because the rocket's going up. And the symbol for escape velocity is V subscript ESC for escape. The escape velocity depends upon two properties. Properties of the planet, not the rocket. It depends upon the radius of the planet, and it depends upon the mass of the planet. The escape velocity formula is V escape is equal to the big square root of 2 times g times the mass of the planet divided by the radius of the planet. I will explain all of this in our next class more carefully. For now, let's just kind of beast it, all right? Now, Emily, I'm ready for you to read the problem. We're just going to do part A.
Just part A?
Yep.
The surface of Mars.
So the question was like, find the escape velocity for the following objects, right?
Calculate the escape velocity from each of the following using the data as needed from Appendix E, A, the surface of Mars.
Okay, luckily for you guys, I know some data on Mars off the top of my head. Wait, do I? I'm a little groggy today. The mass of Mars is 6 times 10 to the 23 kilograms. Mars is like 1/10 the mass of Earth. Ah, nuts. Okay. I guess I know its radius is 3,400 kilometers. Mass of Mars. Mr. Google can help me. Oh, look, 6 times 10 to the 23 kilograms. I was right. And the radius of Mars should be 3,400 kilometers. Oh, miles. That's lame. That's so lame. Who wants to know miles? It's 3,400 kilometers. I know this. Yeah, 3,400 kilometers. Okay, I knew the data. I just doubted myself for a second. The mass of Mars is 6 times 10 to the 23 kilograms. The radius of Mars is 3,400 kilometers. How good are you guys? Can you convert that to meters in one shot? Can you do it in your head? How many meters is that? Yeah, Daniel and Devin know how to do it right away. 3.4 times 10 to the 6. And you could use dimensional analysis to get that if you wanted. Okay, let's set up our formula. The escape velocity of Mars, you guys are nice and good, is the square root of 2 times 7 times 10 to the minus 11 meters cubed per kilogram per second squared times the mass of Mars, 6 times 10 to the 23rd kilograms, divide by 3.4 million meters. Punch them up. Christopher, why don't you just tell me what you got? Because I want to hear you guys round it and stuff. Sometimes you guys get the right answer, but you don't even know how to say what you got.
5,000. Do I want to like round it up that much, or?
That's okay. Yeah. What was it? 5,000 to 2 sig figs, or I think it's actually
Yeah, yeah, to 2 sig figs because I got 4,970.
Okay, cool.
4,971.
So, but what are the units, Christopher, of this escape velocity?
Wait, so I thought we wanted 2 sig figs.
Yeah, but you know what's funny about the number 5,000? That second zero could be significant, but you wouldn't know it because it's significant to 2 sig figs. This is an ambiguity with significant figures, and it's why that scientists always put all answers in scientific notation in professional grade research papers. They don't want to leave any room for doubt. So a professional scientist would write this as 5.0 times 10 to the 3, so that the reader would understand that the second zero is significant, but the others were not. Because the answer he got was something like 4,987 or something, right? So if that
No,
round,
yeah, I understand now. When you put into scientific notation, it makes sense.
right. We have it. For us, we are kind of playing a little fast and loose with the siggy figgies. You know, like, look, you know, big G is actually 6.67, but that was TMI, so I just made it 7. So we can play a little loose. You're asking the right questions, whoever you are. I want to know what the units are, though. Christopher, did you ever figure it out?
Okay, I'm gonna guess that it's meters per second.
That's right. Oh, Blair, yes, Christopher, but Blair, I want to talk to Blair for a second. Check out these moves, Blair. Blair is actually sitting there and canceling the units, I can tell. Blair sees that kilograms cancel with kilograms, check. Blair sees that meters cancels with 1 meters, leaving not just meters squared per second square, Blair, but the square root of meters squared per second square. The square root distributes to both the meter squared and the second squared, leaving us proper ass units of velocity, 5,000 meters per second. You just learned something. That was cool. How many kilometers per second is that? It's customary to convert.
5 kilometers per second.
Very good. Very good. Or 5 clicks per second. That's the escape velocity from Mars. Now, I would love to tell you some anecdotes about that, but I'm guessing probably correctly that you guys are totally cooked, and I understand that. Yep, that was a hard homework. Guys, they will not always be that hard. These last 2 homeworks were kind of rough. Part of the reason they're rough is because you're all still learning, okay? But they're going to get smoother from here on out. Don't you worry. So you learned a lot today. On Tuesday, we will enhance upon these themes and transition into our chapter on light and atoms. I still haven't made up my mind about Tuesday's lab. I'm either going to do another problem on the International Space Station, or I might do the inverse square law. It depends where we are at during our lecture, what you guys are ready for. Okay, so do you guys feel confident that you'll be able to, Caitlin's already taken a photo. You're going to submit that right away, right, Kate? Okay, and the rest of you guys too, right? You're going to make it look nice. It's going to be right side up and all that stuff. It's probably going to be a couple pages long.
Aye, Captain.
All right, Wyatt. Thanks for sticking with me to the end. Yeah, Devin, I am ready for this weekend to begin. Thursday is the new Friday. Okay, to all of you out there in the night class, like, comment, subscribe, and please turn in your homeworks. I'm stopping the recording now.